Graph is one of the most widely used data structures in programming and is often asked in coding interviews as well. Hi, my name is Prateek, and in this tutorial we'll be understanding the basics of graphs, its applications in various domains, and its representations such as adjacency list, adjacency matrix. In the next set of videos, we will be diving deep into graph algorithms and learn to code them. But before we get started, make sure you check out free masterclasses on Scalar's event page to learn from industry leading experts. Also, subscribe to our channel if you haven't done already. Let's begin with the tutorial. So let us talk about graph. So graph is a network like data structure consisting of nodes and edges. So it is a data structure, that means it is able to hold data, and the data is in the form of a network. Okay, and consisting of nodes and edges. So if I look at this figure, all these circles, they represent a node, and all these lines, they are representing a connection between these two nodes. For example, this edge is connecting node 4 and 25. So can we think of any real life example where the data might have connections in between certain objects? Of course, yes. If we talk about cities, then cities are connected with each other through connections which we call as roads. If we talk about a social media graph, for example, this is person A and he is connected with a person B, and A is also connected with a C. So we say B and C, they are friends of A, or A and B are connected, A and C are connected. If I talk about this person D, is it connected to A? We say no. The person A is not connected with D, or D is not connected with A, because there is no direct edge in between them. So if I add a edge, they also become direct connections. So there can be many applications in real life where graphs can play an important role. So let us try to understand the applications first, then we will dive deeper into the implementation and coding. So graphs, as I said, they are used in many real life applications and they represent a network of nodes. Such a network of nodes can be a network of cities, a network of places, landmarks, anything. It can also be an electrical circuit. When you use your mobile phones, it has something called as a circuit. Okay, it has a motherboard on which you have certain elements, certain small embedded systems on it, and there is a wire connecting these any elements. So it is possible that we want to find out the most optimal route for the wire so that we can reduce the cost. Okay, because it is a copper wiring, it can be expensive. It can be a graph algorithm can be used here to minimize the total length of the wire that can be used to connect all the components in this circuit. And of course, social media networks, we have just discussed that Facebook, Twitter, LinkedIn, all these networks, they can represent graphs. So let us go into the applications in little more detail. The first example is an example of shortest paths. We often use apps like Google Maps, Uber, Ola, and many other apps to compute to in our daily life. Okay, so these apps, they try to figure out what is the shortest path between the set of nodes that are there, and should I go from this route or should I go from this route. If you want to do such a calculation, okay, if you want to go from source to a destination, then what path would be best can be easily devised using a shortest path algorithm known as Dijkstra's shortest path algorithm. We will discuss that algorithm in this series. Then of course, if you want to book flights, okay, you want to say, okay, I have to go to this region. Maybe there is a flight which costs 80 and there is a flight which costs 20. Should I take this flight or should I take these three flights? So maybe they are cheaper but they are taking more time. So there might be trade-offs. Again, you have to look at what you want. What is your requirement? Do you want to optimize for time or do you want to optimize for the total cost of travel? The social media networks I have discussed. So I will give you one more example. In some networks, when you connect with a person, for example, Facebook, so if A and B are friends, then this connection is bidirectional. That means A is connected with B, B is connected with A. But in some other networks, this connection is having a direction. For example, on Twitter, if A follows B, it does not mean B is also following A. So these edges, they can be bidirectional or they can be one directional. So we call such a graph as a directed graph or directed edges. Okay, so this graph has directed edges because A is following C and B, but B is not following this. So in such a case, this is called as a directed edge. And in example of Facebook, it is called as a undirected edge because there is no fixed direction. If A and B are friends, then B is a friend of A and A is also a friend of B, right? Now these kind of representations, the graph like representation is important to build algorithms. If you want to find mutual friends, if you want to generate news feed, so for A, it will see the post from B and C. If B is following someone, then this person's post will not be visible to A. So all these algorithms require graph like representation of the objects involved. Then there is also something called as shortest round trip. If you think of if you think of something called as a school van, okay, what is the purpose of school van? It will start from school and it will drop all the children on the way and it will come back to its location. So in this case, what is happening? We are doing a cyclic tour. We are coming to the source by covering all the points in the city where we need to drop the children. Now it is possible that multiple routes can be devised, but we want to devise a route which costs minimum. So such route design can be used in for Amazon delivery vans, for school vans, and this is a very famous problem in graphs called as traveling salesman problem. We will also discuss this problem in the coming series. Let us talk about one more application. So when you are installing software, you might have seen that the software is installing list of dependencies in a certain order. For example, you have to install a software X. For X, you need something called as, let's say, C. C is dependent upon something called as B. B is dependent upon A. And there is something called as D. X is dependent upon D and D is also dependent upon A and B, right? Now, in such a scenario, if I have to install the dependencies, what is the first thing I will install? Of course, I will install A. If I install A, then B and D, they do not have any dependency. So either I can go with B or I can go with D. So I can install B and D. If I have installed B and D, then X has only one dependency, that is C. So I can install C and then I can install X. So if I install the dependencies in this order, right, my software will be installed correctly. So this kind of a graph, it is called as dependency graph, and it is an example of a directed acyclic graph. That means there is no cycle, it is directed. And from this graph, we need to figure out what is the correct order of installation of software, right? So it is often used while installing software on systems, on servers, when you're installing libraries and modules. They follow this particular order, and this dependency graph can be easily created using a graph algorithm called as topological sorting. We will learn about this algorithm in the coming series of videos. Okay, so that is another application of graph. So let us talk about one more application, that is routing algorithms. So Bellman-Ford is a very popular graph algorithm that is also used in finding shortest paths. Now this algorithm is also used in routing algorithms. So when you know the world has lot of routers, right? And these routers are continuously exchanging data packets. So which data packet should go there and what is the shortest time in which it can reach to the desired location? So all this routing is done using a distributed version of Bellman-Ford algorithm, which is again a very interesting algorithm in itself. So let us talk about one more application. So if some of you have done machine learning, then you know in deep learning, the deep learning models, they do gradient computation, which is an important step in training of the machine learning models. Okay, so these gradients are used in backpropagation to adjust the model parameters, and the way these libraries like TensorFlow, PyTorch, they build a computation graph of these gradients so that the computation can be optimized. So you do not need to worry about how to construct the graph. The libraries like TensorFlow, PyTorch, they automatically do it for you. Again, this is inspired from the idea of graphs itself. And in traditional computer vision, what happened? Image segmentation algorithms were used, which were based upon the concept of network flow, which is again a graph based algorithm. So if you do not know what is image segmentation, so image segmentation is basically extracting out objects from an image. It's like drawing a boundary on an object that is like one entity. In case of this example, the car is one object, the building is another object, this footpath is another object, the road is another object. So these kind of algorithms are often used in self-driven cars, but in today's world we have deep learning techniques for image segmentation. But the traditional way of doing this segmentation was based upon a graph algorithm called network flow. Again, let's do one more application in web crawler. So basically, when you want to build a web crawler, for example, you want to crawl amazon.com and you want to scrap the entire website. So when you go to amazon.com, what happens? You load the code is loaded in the browser. So in the code, you will see it there are a lot of products, and with each product, there is a hyperlink. So you want to go and scrap all those products. So what do? You build a web scraper that reads these links, adds them into queue. Maybe this is some TV button. Okay, so you go to that page, it opens up, and then again there are many links here. So you can also use these links to crawl further, right? So it's like a tree traversal. So web crawlers use breadth first search to crawl the web. So if you have built a web scraper, you would have know that you often do a BFS like thing, and you traverse the DOM tree, and a tree is also a graph. Okay, a tree does not contain a cycle, but it is also a graph example. So let us do one more application. So nowadays, we also have databases that are inspired from the idea of graphs. One such database is called Neo4j. So these kind of databases are used in recommendation engines, fraud detection, and many AI-based applications. Apart from it, there are a lot of other applications of graphs, such as in linguistics, social sciences, biology, neuroscience, atomic and molecular structure, computer processing, flood fill, and more. So what is this flood fill? This is an interesting application I often cover in my course. When you use the paint bucket tool like this and you drop it in an object, it automatically fills the color till it hits the boundary, like you can see here, right? So this again is an example of graph, and this matrix is an example of a 2D implicit. It's a 2D matrix which is representing a implicit graph. So we will discuss about what is an implicit graph and how do we build algorithms on implicit graph. That will be covered as well. So that's about the applications. Next, we will dive into the more technical concepts and understand how a graph can actually be created and stored inside the memory. Next thing I want to talk about in graphs is classification of graphs. Though we have talked briefly about weighted and unweighted graphs, let us try to understand with some more examples. Basically, there are two criteria for classifying graphs. One is weight of edges. There can be graphs in which there is no weight associated with the edge. That means each edge is treated equally. Each has a unit cost. Okay, you can say, okay, it is a unweighted graph. Such a graph is called as unweighted graph. But it can be scenario, for example, if you talk about roads, so each road might have a length, or it might have a time to travel from B to C, right? So some kind of weight or maybe some kind of fuel cost. So we can say that in such a scenario, each edge is having a different weight, and we need to store that weight as well. Okay, so earlier if I'm representing a edge as a comma b in an unweighted graph, now I have to represent edge as a comma b comma 10. That means the time to travel from A to B, or the edge weight from A to B. So this is a case of a weighted graph, right? That means in the implementation also, we will have to store this weight associated with the each edge, and then there is direction of edges. Now there can be scenarios where the edges are not having any specific direction. For example, talk about Facebook friends. If A and B are connected, they are connected. That means A is a friend of B, B is a friend of A. But edges can have a certain direction. For example, a Twitter graph. So if A is following B, does not mean that B is also following A. So in this case, edge will have a certain direction. That means A is following B and A is following C. and B is following C, something like this. This is an example of a directed graph, and wait, so this is an example of undirected graph. Let us look at some more examples. Okay, so we have discussed graphs whose edges or paths can have values associated with them. They will be called as weighted graphs. Edge value can represent either the weight or some kind of cost or length of that path. For example, in roads it might be the distance in kilometers. So directed undirected graph we have already discussed. Graph edges can have specific direction attached to them. They're called as directed graphs. Okay, now in such a scenario you might have two-way edges. For example, from 1 to 2 there is an edge, from 2 to 1 there can be edge as well, and it is possible a different weight is associated with each of it edge. For example, we are going from Delhi to Bangalore via flight. Now this flight might cost you 4k, but this flight might cost you 5k. So this is an example of a directed and a weighted graph. In an undirected graph, there is no direction of the edge. That means you can travel in both directions. You can go from A to B, you can go from B to A, for example, in roads. Okay, so I hope you're able to understand through these examples. So let us try to make a matrix, and let's summarize, right? So I can say graph can have weights, weighted graphs, or unweighted graph. They can have direction or they can be undirected. Okay, so what would be an example of a directed and a weighted graph? For example, from A to B, okay, and there is a cost associated with it. This can be your graph of different flights across cities, because flights will have a cost and they will have a direction. So if there is a flight from A to B, it is possible that there is no flight from B to A, or B to A flight has a different cost. This will be a directed and a weighted graph. Let's look at an example of a directed and unweighted graph. I talked about topological sorting, in which we said that there are certain tasks and there are dependencies. For example, B is dependent upon A, C is also dependent upon A, and C is also dependent upon B. So this is an example of a directed acyclic graph. Okay, so this is an example of a dependency graph. In this graph, there is a direction, but there is no weight. So it is an example of directed and unweighted graph. So an example is dependency graph. Okay. Then there is an example of undirected but weighted graph. So I want a graph in which there is no direction, but there is a weight. Maybe the road network, I can say, okay, the roads are generally two-way. So there is a cost, so there is a weight, but there is no direction. So 100, 200, 10, 20. This is an example of a undirected and a weighted graph. Then undirected and unweighted graph. So that means no direction and no weights as well. So it could be simple Facebook graph in which you are representing who is connected with whom. A and D, they are friends. So there is no weight. So maybe a Facebook friends graph, okay, or Facebook network. So it is possible that it is unweighted, but depending upon how Facebook implements it, this graph can also become weighted. Facebook might represent a score, a friendship score on each edge, how strong these two people are, how strong their bond is. So it is possible that this graph can be made as weighted also. So I hope classification of graphs is clear through these examples. And next we will dive into the implementation, how to create a graph and store it on your RAM. Now the next question arises, how do we actually create this data structure and how do we work with it? So there are three common representations for graph. One is called as edge list, one is called as adjacency matrix, and one is called as adjacency list. We will go over all of them one by one. Each representation has its own set of advantages and disadvantages. But in general, this representation, which is called adjacency list, this is the most popular and most commonly used in many algorithms. But this does not mean that edge list is useful or adjacency matrix is useless. They are also useful. They have their specific applications in certain type of algorithms. So let us discuss edge list first. And what is a edge list? So in a edge list, we represent graph in terms of list of edges, right? So suppose we have vertices A, B, C, D. So we will make a list of vertices, and if we have edges, we will note down what edges we have. We have AB, so AB is an edge. We have AC, we store that. We have AD, we store that. We have BC, we store that. We have CD, we store that. So right now I'm assuming this is a undirected graph. So when AB is an edge, it also means BA edge is also there. That means if you can go from A to B, you can also go from B to A as well, right? Similarly, if you can go from A to C, you can go from C to A as well, right? So in my code, I will be storing two copies. AD is there, DA is there, BC is there, CB is there, DC is there, right? So I'll be storing it like this. That will be more helpful, because if I am at D and I want to look at what nodes I can visit, so I can clearly look at this. There is an edge from D to A and there is an edge from D to C, right? So I can look at this. Or you can say, okay, I'll iterate through the whole list. Of course, you will have to iterate through the whole list and you have to look at what pairs contain D, right? From that, you can get this information from D where you can go, right? But this kind of representation is pretty, I would say, inefficient if you have to find whether there is an edge between, let's say, B and D. I want to see whether there is an edge from B to D. The answer is it is inefficient, because you have to do a linear search over the whole list. So that means you have to spend order of e time looking for whether such an edge exists or not, right? Similarly, if you have to do an operation like, okay, give me the neighbors, immediate neighbors of B, right? This is now a very common operation in graph algorithms such as BFS, DFS, Dijkstra's. We often need this operation, right? So neighbors of B. So what are the neighbors of B? So again, you cannot tell directly. You have to iterate over the whole edge list to find out what are the neighbors of B. Again, this operation is going to be inefficient. It is going to take order of e time, right? But one thing this edge list is good at, for example, suppose this this graph was a, let's say, a weighted graph, let's say 10, 5, 2, 1, 6, right? And I want to pick edges based upon their weight, right? So now in such a scenario, I will be storing three things in an edge. So I will be storing A, B followed by 2. I will be storing A, C followed by the weight, right? In case of a weighted graph, I need to store three things, right? And so on. Maybe I want to pick edges based upon their weight. So what I can do, if I've stored all edges in the form of list, I can easily do sorting on this list. Okay, I can do sorting on the list in like e log e time, right? E log e time. And I can pick edges maybe based upon their weight, right? So, or according to some criteria, right? So maybe I want to do sorting on the list based upon weight of edges. So this kind of algorithm is actually helpful when we deal with a topic that is called as minimum spanning tree, right? So when we are building a minimum spanning tree algorithm, we actually need to pick edges based upon weight. So in such an algorithm, we will go with the edge list kind of a representation, right? So that means this representation is also useful, but it depends upon the algorithm. What kind of operation do we want? Do we want to get neighbors of a node, or do we want to sort edges? So if we want to sort edges, then edge list is the representation that we will use. So I hope you are able to understand edge list. And now in the next video, and now we will discuss the code of edge list. So I'm going to show you how we can create a graph using edge list. So I am in my IntelliJ IDE and I'm going to create a class called as graph using edge list. This class will be responsible for holding the data of the graph. So effectively what I'm going to do is I'm going to keep things little simple. I'm going to fix number of nodes. Let's say number of nodes is given as input by the user. Let's say user says 4 nodes. So I'm not going to take input the names of nodes. I'm going to assume that the nodes are always numbered from 0 to n minus 1. So this is from 0 to 3, right? This is something which is very common in many coding problems, and we often we make this assumption, okay? And you can also verify from the problem statement. If this is not the case, then we will discuss it separately, right? So number of nodes are 4, and let's say the graph looks like this: 0, 1, 2, 3, right? So what is expected in the input? that you will be given how many edges are there. So number of edges will be input, that is also 4, and then you will be given the names of edges. So 0 comma 1 is one edge, 0 comma 3 is another edge, 1 comma 2 is another edge, 2 comma 3 is another edge. So you will be given these numbers input. So what is our expectation? That this graph should be able to hold these pair of edges. So 0 comma 1 I want to hold, 0 comma 3 I want to hold, 1 comma 2 I want to hold, and 2 comma 3 I want to hold, right? Now if you look at this list, can you visualize this graph? Of course yes, right? That means this information is sufficient to store this graph, right? So what I'm going to do in this graph class is I'm going to make a list which is able to hold a following edge, right? Now it is possible that each edge might have a certain weight, let's say some weight w1, w2, w3, w4, right? So in such a scenario I can add w1, w2, w3. It will be list of edge where each edge object is a collection of 3 numbers in this case, right? So what we can do is we can define a class called as edge, right? We can define a class called as edge, right? And in this class I can have 3 things. One is maybe the source, so I call it as u. I have v and I have weight, right? So that means the triplet. So if there is an edge from u to v with a weight w, I'm going to store a triplet u v w, and I'm going to create an edge object out of it, right? Then I can make a list of edges. So I hope you understood the concept. Let us dive into coding. So I need a constructor for the edge class. So the constructor is going to expect u, v, and w, right, for one edge object. So I can say this dot u equals u, this dot v equals v, this dot weight equals weight, right? So later on I want to print the edges, so I might need a method to display an edge, right? So I can just use the toString method, which is going to show me, which is going to print, which is going to return a string representation for this edge. So this will be helpful when we are going to print the edge. So if I want to do s out an edge, I will see that the edge will be printed like this: u equal to something, v equal to something, and weight equal to something. This overrides the default toString method, right? And it is auto generated by the id for me, right? So I have the toString method with me, right? This will be helpful if I'm going to display the graph. That means I'm going to display this edge list in the output. So I don't have to, I don't have to write for each edge. I don't have to do this work, because this method will be called when I'm going to print it. So I can simply say s out some edge, right? So something like this we can do. So now coming to this actual class, right? So let's make this class as public. In this class, what information it needs to hold? It needs to hold how many nodes we have, number of vertices. Number of edges is optional because it can be judged by the length of this list, right? So user is going to enter the edges and we are going to store them, right? So that is simple. And so let's have a constructor, right? So the construct, and apart from it we need a list of edges, right? So list of the type edges L. Let's create the constructor graph using edge list. So in this constructor I'm going to get number of vertices which I can initialize. So this will be list of edge. So I can say this dot v equal to v, and I also need to create this list. So L is a new list, so it can be a linked list or an array list, and I can say it is an empty list, right? So when a graph is created, it knows how many vertices it has and it creates an empty linked list. Okay, now I want to add edges in this graph. So maybe I need to create some method add edge u comma v and weight, right? I want to push an edge into this graph. So I can simply say uh, if there is an edge from u to v, so I can say l dot add. What I should add? I should add a new edge which goes from u to v and is having a following weight. So I'm doing it for a directed graph, right? I'm doing it for a directed graph. So I think this implementation looks complete to me. Now let us test our implementation by going to main, right? So here what I need to do, I need to create a graph object, right? Which I am doing, right? And then I'm saying that fine. Okay, so here I've passed one more parameter which is going to tell whether the graph is directed graph or undirected graph. So this is an optional thing. If you want to accept that okay, this is a directed graph, then you can add just this edge. But if it is an undirected graph, you also need to do one more uh, line of code where you are adding the edge from U to V, right? So you are saying that okay, A and B are connected. That means A is a friend of B. There is an edge from A to B, but there is also an edge from B to A, right? So you can do this thing in case of a undirected graph. So that can be handled by putting a if condition here. But for now, I'm keeping things simple and I will modify this code a little bit. Earlier, I did it for undirected graph, right? So it's just a signal to the graph whether you want to add this edge like one time or two times, right? And now I want to display the graph. I basically want to display the edge list, right? So I created a graph object using this class new graph. I initialize the number of vertices, which actually we are not using as of now, but this might be helpful in future, right? For some other use case. Now if I want to display this edge list, so I can say okay, void display. Okay, or let me see if I can do a toString thing here, right? So here I'm going to modify this, right? I'm going to, or this is fine actually, this is fine. So it is going to return a list. Let's see what does it return, right? So I'm going to say sout graph, show me the graph, right? So let's go and run this code. Okay, so this graph says that okay, I know two things. I have vertices which are 4 and I have a list of edges which is this list. Okay, so there is an edge from 0 to 1 with weight 10. So 0 to 1 weight 10, 0 to 2 weight 20, 0 to 2 weight 20, 1 to 2 weight 30, right? So you can see this is completely fine and we are able to see uh, the edge list that we have implemented. So that is the idea behind edge list. Now you can use this edge list to do sorting. So right now I have hard coded values here, but what you can do, you can ask the number of edges, put a for loop, take input those edges, and inside the loop you can call this function g.addEdge, and this is going to add all the edges in your graph, right? So in generally, I've discussed how the input is given, number of nodes is given, number of edges is given, followed by list of edges is given, right? So pairs like 0, 1, 10, followed by next pair 0, 2, 20, right? This will be input. You can scan it and call g.addEdge to add it in your graph, right? So I hope this representation is clear. Next, we will discuss another implementation. The next representation of a graph, it is called as adjacency matrix. So what is this? It is a 2D matrix which is of the size v cross v, where v is the number of vertices of the graph. The number of elements in the matrix indicate whether pairs of the elements of the matrix, actually not the number of elements. The element of the matrix indicates whether pairs of vertices are adjacent or not. Basically, if there is an edge from 1 comma 2, right? So what we will do, we will have a adjacency matrix. Okay, so in this case there are 5 nodes, so there is a 5 cross 5 matrix, right? And there is an edge from 1 comma 2. So what we are doing, we are saying that matrix of 1 comma 2 will be true. So if it is a unweighted graph, there is no weight, so I can simply set this edge as true. So 1 comma 2 is true, or it is 1, right? And similarly, if it is a undirected graph, there is no direction, so matrix of 2 comma 1 is also true, right? So this value is also true. So this value 1 comma 5, this is 0. So this basically indicates there is no edge from 1 to 5, right? So if there is an edge from x comma y, then in my matrix of x comma y will be set to 1, and matrix of y comma x will also be set to 1. That indicates that x and y, they are connected, right? So this is pretty simple. And the problem with this approach is that as your n grows, right? So if let's say you have 1000 nodes, right? Your matrix will be of the size n square, right? So that means it will have 10 power 6 elements. So if n is let's say 10 power 7, your matrix will be of the size 10 power 14. You won't be able to hold this big matrix in your memory, right? So it is not suitable for large number of nodes. Okay, it is suitable for small number of nodes, but again there are certain advantages and disadvantages for this, right? One disadvantage is that you are going to waste a lot of space. So in most of the graphs, if you have n nodes, you might not have n square edges. That means lot of zeros will be there in the matrix, which is leading to space wastage. Secondly, if you want to find neighbors of 1, what nodes are connected with 1? There is no way. You have to iterate over this whole list, which is going to take order of v time, right? Because there are v vertices here. You have to go to each vertex and check whether one is connected with it or not, right? That is again a problem. We do not want to go to 5 because one is not connected with 5, but we are still iterating, right? So this is a major disadvantage. That means you cannot get neighbors of a node. In order to get neighbors of node, you have to spend order of v time, which is not very efficient operation, right? But there is one advantage as well. So what is the advantage? If I have to check if there is an edge between 1 comma 3, right? So that check can be order 1. Why? Because you just need to go to 1 comma 3, this index, and check yes, this value is 1. So you can check yes, this value is 1. So that means I can figure out whether an edge is present between two nodes or not in just order 1 time, right? Now you might ask, what if the graph was a weighted graph? 1 comma 2 was having, let's say, w weight. So in such a scenario, instead of storing 0 or 1 here, you will store 0 followed by weight, right? 0 and weight. So 1 comma 2 has having w weight, so 2 comma 1 is also having w weight, right? So you can store integer values. 2 comma 5 has 8 weight, so 2 comma 5 you can put this value as 8, and 5 comma 2 as also 8, right? So depending upon the use case, this matrix can be an integer matrix or it can be a boolean matrix, right? So I hope you understand the concept of adjacency matrix. Now let us look at the implementation of adjacency matrix. Let us implement graph using adjacency matrix. So again, I will have to keep number of vertices and I will have to keep a boolean matrix. So I can say a boolean some matrix, let's say called adjacency matrix, and we will initialize this matrix in the constructor, right? So I have graph using adjacency matrix. I'm getting the number of vertices. This dot v equals v, and adjacency matrix equals new boolean of the size v cross v, right? So I hope this matrix, this initialization is clear. By default, I think all the values would be false, and now we can write the add edge function, right? So I'm not going to take the weighted graph because I've taken a boolean matrix. So I will take only two parameters, the edge from u to v, and also I'm assuming the graph is a undirected graph, right? But if you have a directed graph, then it is even easier, right? So if there is an edge from u to v, what I need to do in the matrix for the uth row and the vth column, I need to mark this as true. So I can say adjacency matrix of u comma v will be marked as true, rest everything is false, right? And adjacency matrix of v comma u, this is also true, right? So the other way around we also have to do, right? So that's it. Now what we need to do, we need to test our code, right? This adds an edge to our graph, and now we can have a display method, right? That is going to display the matrix. So I can add a toString method here, which is going to display the vertices and the adjacency matrix. Let's go to main here, and now I have to create a graph using adjacency matrix. So I've added a few edges, and now let us go and run this code, and let's see what output do we get. Now we are getting, okay, in this graph object we have 4 vertices, And now adjacency matrix is being displayed like this. So this is actually how a 2D array is stored in Java, right? So if I talk about a 2D array, a 2D array is a 1D array of rows, right? And each row is actually is storing the address of an array, right? This is how it is being done, right? This is how it is actually done. 2D array is an array of rows, and each row is, let's say this row is 30C, this is 97D, right? So what we are printing is, we are printing the address of each row of the array, right? So this is the address of a 1D array, 0th row, first row, second row, and third row. If I want to handle this in a correct manner, right, so I have to say that we do not want to convert this 2D matrix into string directly. We have to use a method called deep to string that will actually iterate deeply into each row, and then it will convert the contents into the string, right? So I'll do it like this. This will actually give me the string like representation of the full 2D array, right? Let's go and run this code once again and see what do we get. Yeah, this time I'm getting the correct adjacency matrix. So I will draw it for you. So what I did, I give 4 vertices, let's say 0, 1, 2 and 3. Then I said 1 and 2 are connected, fine. 0 and 3 they are connected, okay. 1 and 3 are connected, okay. And 2 and 3 they are connected, okay. So this is how the graph looks like. And then I have a 4 cross 4 matrix, 0 1 2 3, 0 1 2 3. So it is false 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 true. So here I have a true here, false false true true. So here I have true true, false true false true. So true true. Then I have true 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 false, t t t. So if you look at this 0, so 0 is only connected with 3, so we have a true here. Then look at 1, 1 is connected with 2 and 3, so 1 is connected with 2 and 3, correct? Look at 2, 2 is connected with 1 and 3, 2 is connected with 1 and 3, correct? Look at 3, 3 is connected with 0, 1, 2, so 0, 1 and 2, yes. This is a correct representation of the adjacency matrix for this graph. So I hope you understood this concept, pretty easy, nothing fancy in it. And you can easily modify the code for a directed graph by making this as a integer matrix and putting the weight here, right? So that's all. Next we will discuss adjacency list. Now let us talk about one more implementation of graph that is called as adjacency list. So this is the most widely and most common used representation in many graph algorithms. What do we do in this representation? The adjacency list represents a graph as an array of linked lists. The index of the array represents a node. So we will try to understand. Now suppose I have 1 to 2, there is an edge, right? So what I really want to do is that with node 1, I actually want to store all the neighbors of 1. So 1 is connected with 2, 1 is connected with 3, 1 is connected with 4, right? So basically there is a key value mapping. So key is 1, value is the list of nodes with which it is connected. One way to store it is that we create an array. Now suppose there are 5 nodes. So here they have assumed a 1 based indexing, but in our code there will be a 0 based indexing, right? What it is saying that it is a linked list, right? So if you talk about 1, 1 is connected with 2, 3, 4. Similarly, if you talk about 2, 2 is connected with 1, 3 and 5. So I know 2 is connected with 1, 3 and 5. 3 is connected with 4 and 2, right? So and 1 also, so it is connected with 1, 2 and 4. 4 is connected with 1 and 3, and 5 is connected with 2, right? So each of this is like a linked list. We can definitely add more to this linked list. For example, if 5 and 6 are connected, so I can say, okay, in linked list of 5 you can add 6, and in 6, at the 6th position you can add 5. Okay, so why we are using this linked list? Because it is easy to add into this, so we can easily do a add operation, right? But how many linked lists do we need? Do we need one linked list? No, we need an array of linked lists. So this data structure is an array of linked list, right? So right now we are assuming a one based indexing, but it will be zero based indexing. If I talk about array of one is nothing but it is a list. What about array of 2? Array of 2 is nothing but it is a list. And what does array of 2 denote? Array of 2 denotes a list containing neighbors of 2, right? So if we implement this, right? So what we are going to store? We are going to store this, and we are going to form an array out of it, right? So this is what an array of lists look like. Some of you might ask, what happens if nodes are not numbered 1, 2, 3? Suppose they are numbered as Delhi, Mumbai, Jaipur. In that case, instead of using an array of lists, you can also create a hash map, right? Where the key is a string and the value is a list of string. That is also possible, right? That is also a way to implement a adjacency list. So in case of zero based numbering, it becomes easy because array indexes are numbers themselves. But if you have something complex like Delhi, Mumbai, Jaipur, Ahmedabad, you can also use a hash map in place of it, right? So I hope you are able to understand this concept. Now let us talk about advantages of this representation. So the first advantage is efficient storage. We are not wasting any space, unlike we did in adjacency matrix, right? So we are only storing the value of edges where the edges actually exist. So it is efficient in terms of storage, right? They are also useful for storing sparse graphs. That means um, which have much lesser edges compared to, like, what will be a dense graph. So if you have five vertices and you have, let's say, v square edges, in that case that means every node is connected with everyone. In that case adjacency matrix can be easily used, right? But if you have five vertices, seven edges, it's kind of a sparse graph, right? Number of edges is much less than v square, right? And the biggest advantage is efficient retrieval of neighbors. As I told you that this is an important operation that we frequently do in algorithms like BFS and DFS. We can easily find neighbors of any node. If I ask you, okay, find neighbors of 3, what you need to do? You need to go to array of 3, which is an order 1 operation, and then you need to iterate on this list. So basically in order of neighbors time, if 3 has 3 neighbors out of 100 nodes, you can get those 3 neighbors in 3 units of time. You don't have to traverse the whole list of nodes, right? So this is a very efficient operation. Because of these two reasons, it is a very widely used. One is efficient storage, second is efficient retrieval of neighbors. This makes adjacency list a popular choice for graph representation and is used in many algorithms such as BFS, DFS, shortest path algorithms, and much more. Now let us discuss implementation of adjacency list. So let us start implementing graph using adjacency list. So we are discussing adjacency list implementation for the graph. So one thing we need is the number of vertices. Next, what do we need? We need an array of linked list. So how do I create it? I can say list of what? List of integers. If I simply write adjacency list, this makes one list object, but I need an array, right? Now I need to initialize this array inside. Okay, this will be integer here, right? Because my collections does not accept primitive data types. I need to initialize this object in the constructor itself. What is the size of this list? That will be known when we are creating the graph object. So I can get the number of vertices and I can say this dot v equals v, and I can say this dot adjacency list, this is equal to new linked list of integer. And how many objects do I need? I need v number of objects. Okay, so I have created an array in which this adjacency list, right? But right now this object is not created, right? Only an array is created. So what I need to create? I need to create a linked list at each index. So how do I do it? So I can say, okay, I will iterate over this I equal to 0, I less than v, I plus plus, right? So basically, when I say I'm creating this array, that means the array bucket can hold the address of a linked list. But right now that is null, right? So what do I want? I want this bucket to hold the address of a linked list object. So how do I create this linked list object? I have to use new, right? I have to say adjacency list of I, this is equal to new linked list. This actually creates an array in which each element is a linked list object, right? So this is the correct way of constructing a adjacency list. Now what do I need to do? I need to add elements into the linked list, right? So I will have a function called void add edge. So edges from u to v. What do I do now? I can say, okay, if there is an edge from u to v, what should I will do? And maybe I can accept, is it a undirected graph, right? If it is true, I will also add an edge from v to u, right? So I can say adjacency list of u dot add v, something like this. And if it is a undirected graph, I can say adjacency list of v. Oh, it will be boolean, right? Bool is in C++. Adjacency list of v dot add, something like this. Basically what I'm saying that go and add an edge from 1 comma 2. So 0 1 2 3. So in first link list it will add 2, and in second list it will add 1. Then I say okay, go and add 1 comma 3. In first list it will add 3, and in third list it will add 1, something like this. Basically if 1 is connected with 2, 1 is connected with 3. So if I read this, I see 1's neighbors are 2 and 3, right? So if I write it little more clearly, so 2 and 3, they have been added into the linked list which is at the first position, right? So this is how the add edge function looks like. Then I can display the graph, so I can write the toString method which is auto generated. And here, similar to the previous case, normal toString will not work. I want to iterate deeply into the data structure. I will use deep toString method, and this adjacency list will be converted into a string like representation that I can print. Now let us come to our main, which is here, and I have created a graph, right? I'm trying to add edges in it, and I'm trying to print it. So this I have already written before. So I'm just going to run this, and you can see the graph class we have just constructed now, right? Let us try to visualize this graph. So 1 is connected with 2, fine, undirected graph. 0 is connected with 3, okay, 1 is connected with 3, and 2 is connected with 3. So this is how the graph looks like. And now if you talk about the adjacency list, so 0 is connected with 3, okay, 1 is connected with 2 and 3, 1 is connected with 2 and 3, that's correct. So list of 1, it is storing the neighbors of 1. List of 2, so 2 is connected with 1 and 3, absolutely correct. What about 3? 3 is connected with 0 1 and 2. So 3, adjacency list of 3 is storing neighbors of 3. This is how this 2D array, okay, it's not a 2D array, it's a array of linked lists, right? Each linked list is denoting the neighbors of the ith node, right? That is the adjacency list implementation. I hope you are able to understand this implementation. So pretty easy, nothing fancy, nothing difficult. And if you have more complex data, as I told you, instead of having this, you can also have a hash map where key is your this will become your key, and this will be added into the list corresponding to that key, right? That's all for this implementation. Okay, so we have discussed the most commonly used implementations of the graph: adjacency list, adjacency matrix, edge list. There is one more representation that is sometimes convenient for certain type of problems. Okay, so sometimes we are given a graph in which we are saying, okay, there is a 2D matrix, and it is given that each cell is connected with, let's say, the 4 neighbors, something like this, or each connect cell is connected in the 4 neighbors which are of the similar color, right? And you have to do something, right? So in this case, what you have to do, you do not need to construct a graph, you can directly deal with the matrix, right? So if I say, okay, what are the neighbors of this one? Either it will be four-way connectivity, it will be mentioned in the question, then you can go in these directions. or it can be eight-way connectivity. That means the diagonal directions are also included. This kind of representation is helpful in some algorithms like flood fill, right? So what is happening in flood fill? There is a 2D image which is made up of some pixel values, right? So you are filling the color until you hit the black boundary. And how are you finding the neighbors? You are going in this four-way connectivity or doing the eight-way connectivity, right? This is not possible for every type of graph, but certain problems where graph could represent an image, right? Or the neighbors have this kind of relationship where they can be represented using a 2D array, right? So we will deal with these kind of problems in the series, and I hope you learned a lot of concepts from today's video. Again, make sure you like the video and subscribe to our channel before leaving. Thanks a lot. I will see you in the next video. Hello everyone. In this tutorial, we will talk about graph traversals. The first traversal that we will discuss in detail would be breadth first traversal. And in the next tutorial, we will discuss about depth first traversal. Both of these traversals are really important when you are solving problems related to graphs, and they have many real life applications. But before we get started, make sure to check out free masterclasses on Scalar's event page to learn from some of the best industry experts. Link is in the description below. Let's begin with the tutorial. So let us talk about graph traversal first. What is a graph traversal? So graph traversal, also known as graph search, is a way or is a process of visiting each vertex in a graph. Such traversals, as I told you, are classified into two types. One is BFS, which stands for breadth first search, and it is a iterative way to traverse the graph. And second one is a recursive way called depth first search. In this tutorial, we'll focus on BFS and its applications. So BFS actually has many applications, and one of the most commonly used application is finding shortest paths in undirected graphs. We'll also look at such applications in this tutorial. So let us start talking about BFS. So it is a technique for traversing a finite graph. That means the number of nodes in the graph would be finite. And the way it works is it visits the sibling nodes before visiting the child vertices. So what does it mean? If you have something like a node A and it has children like B and C, and then you have some children like D and E, and so on. So the way it works is if you look it in the form of a tree, suppose this graph is a tree. Now this is not a tree because I'm added one more edge here. So the way it works is it will visit this node, then it will come at B, but it will visit sibling of B, that is C next. So it will visit BC, then it will visit D, E, F, G, and so on. So in a way, if you look at in the form of a tree like traversal, it is like a level order traversal that we have done in a tree. But in a graph, it will be quite similar, but there is one catch. The catch is graph contains a cycle, right? We have to make sure that we are not visiting a node which is already visited. For example, from this node 1, if you visit 2 and 2 is connected with 3, 3 is connected with 1, so there is a cycle. If you say okay, I'll visit 1, I'll visit children of 1, that is 2, I'll visit 3, from 3 now you cannot go and visit 1 again, right? So this is something we have to make sure is handled properly by our algorithm. So before I dive deep into the algorithm or into the code, let us try to understand some applications of BFS. BFS is can be used to find all the vertices within a connected component. So we want to see what parts of the graph are connected. It is also used to finding shortest path between two vertices in case of a undirected graph. That means all the edges, sorry, unweighted graph. That means all the edges, they have equal weight. There is no weight assigned to any edge. If it is a weighted graph, then we have to use a different algorithm. It can be used to check a graph for bipartness. It can be used for cycle detection in undirected graphs. It is also used in Ford-Fulkerson algorithm for maximum flow. It is also used in serialization, deserialization of binary tree. It is also used in maze generation algorithms, and it can also be used in algorithms like flood fill. So there are many applications, and that is why understanding this algorithm becomes very important. So let us now dive deep into the algorithm. Now suppose a graph like this is given. So what kind of graph it is? In my case, it is a unweighted graph, and it is also a undirected graph. That means edges don't have any specific direction. If 0 and 2 are connected, 2 and 0 are also connected. So we can go both sides, right? So now in this algorithm, what is the input? The input is a source vertex. That means you are given a starting point. From that point, you have to traverse the whole graph. The starting point could be 0, it could be 3, it could be 6, it could be any node. So just to keep things simple, I'm going to take 0 as my starting point, right? And let me also draw the adjacency list that could be possibly input for this algorithm. So that means 0 is connected with 2 and 1. 1 is connected with 0 and 4. So neighbors of 1 are 0 and 4. Neighbors of 2 are 0, 3 and 4. So 0, 3 and 4. Neighbors of 3, they are 2 and 6. Neighbors of 4, they are 1, 6, 5. So I'll write it as 1, 5, 6. Then I have neighbors of 5, which are only 4, and neighbors of 6, which are 3 and 4, right? One thing I told you, that if you start from this node, right? So what we need to do, we'll be using a queue in this algorithm. You will understand why this queue is going to be very, very helpful. Let me draw a data structure here, which is a queue. Apart from it, we will also need something to maintain whether a node has been visited or not, right? Because the graph contains a cycle, and it is possible that we are coming to the same node again and again, right? So this is a queue. It is a empty queue as of now, right? The queue, you know, it has a FIFO property, first in first out property, right? So it is a FIFO queue here, and apart from it, I'm making one more data structure, which is going to denote whether a node has been visited or not. So 0, 1, 2, 3, 4, 5, 6. I think this is sufficient. We don't need. So we will mark whether a node is visited or not. So right now it is nothing is marked, nothing is visited. We'll start from this node, that is the source node. Let's just assume the source node is 0. We'll mark it and we will put it into the queue. 0 has been visited, 0 goes into the queue, and I am going to mark it as visited. So here the circle denotes the queue has been visited. Now what you will do next? You will look at this adjacency list. You will find out the neighbors of 0. The neighbors of 0 are 2 and 1. So you will pop this node out. The node is 0. You will look at neighbors of 0, that is 2 and 1. You will mark them as visited and put them into the queue. So you, from 0 you can easily visit 2 and you can easily visit 1. What I'm trying to do is I'm marking 1 and 2 as visited, and I'm putting 1 and 2 into the queue. So first I visited 2 and then I visited 1. Both of them, they are into the queue. That means I've marked 1 and 2 as visited. Now what you will do next? Nothing. You simply have to pop out a node from the queue every time and do the same process again. So now you will remove 2. Look at the neighbors of 2, which are 0, 3 and 4. So now 0 is already visited. So you do not do any work at 0. Then 3 and 4. 3 is not visited. You can visit 3. So mark 3 as visited. Put it into the queue and mark 4 as visited and put it into the queue. Okay. Now 2 is gone. 2 has been removed. Next node you will get from the queue, it is going to be 1. So you will remove 1 from the queue and you will mark neighbors of 1 as visited. So neighbors of 1, 0 and 4. So look at 0. 0 is already visited. 4. 4 is also a neighbor. 4 is already visited. So you do not do any work. Right? So in the meanwhile, you can print the nodes that you have seen so far. So you have seen 0, you have seen 2, you have seen 1. Next, you will pop out 3. So remove this node, print this node, look at the neighbors 2 and 6. So 2 is already visited, do nothing at 2. 6 is not visited. So mark 6 as visit, put it into the queue. So you have traversed 6 as well. So 6 is now also into the queue. Next, you will pop 4. So print 4, look at neighbors of 4. The 4 neighbor is 1, which is already visited. Its neighbor is 5, which is not visited. So you will visit it, put it into the queue. 6 is already visited. Nothing to do here, right? Next, you will get 6 from the queue, remove it, print it, And now look at neighbors of 6. Sixth neighbor is only 3 and 4, right? But both of them they're visited, so you will not do any work. So next you will remove 5. 5 neighbor is 4, so this is also removed. 4 is already visited, hence you do not do any work. And now what you can say is that your traversal is done, right? Your traversal is done. So what happened during this traversal? So we visited each node once, and in the worst case we are traveling through all edges once, right? So what we have done, like we have traveled through some edges, and we also checked that from 4 I can go to 1. So we did check this edge, right? We did check this edge. 1 was already visited, so we did not mark anything here, right? So we did not mark anything here. What I'm trying to say is, when you're running this algorithm, each vertex is going into the queue once, and it is coming out of the queue once. And when you're finding the neighbors of a node, you're traveling through all the edges, right? So all the edges are being covered at most twice. For example, neighbor of 4 is 6, neighbor of 6 is 4. So each edge is counted at most 2 times. So if I talk about the overall time complexity of this algorithm, it will be linear in terms of number of nodes and number of edges. This is what we are doing, right? So I hope you have understood the basic BFS idea. Next, we will look at the implementation and code this algorithm. So let us discuss the implementation of BFS. I already have the boilerplate code ready, which is basically adding edges into the graph. So the BFS function is something that I'm going to write now. So return type is void. We do not want to return anything. The method name is BFS, but what we may expect as input is one source node from which we should start doing the BFS for this graph. So this is the graph. So I told you we will be needing 2 data structures, one to maintain whether a node has been visited or not. So I can maintain a Boolean visited array, and this will be a array of size v, where v is the number of vertices in the graph. Next thing I will need would be a data structure q. So in Java we have q as an interface. So I'll create a linked list which provides me with the implementation of q as well. So linked list of integers, we will just call it as q, and I will say this is equal to new linked list. All right, so that are these are the data structures that we will be needing. Now let's start with the algorithm. So in the first step, what I will do, I will start with the source node, mark it as visited, push it into the queue. So I have to do 3 things. Mark it as visited, so visited of source is going to be true. So I will say okay, this is going to be true, and then I will traverse the neighbors of this node. So first thing I will do is I will push this into the queue. So I can say queue dot add last. The node is source. Okay. And second thing I will do is I will mark this as visited. The visited of source, this is going to be true. Now what can I do now? I can say while my queue is not empty. So I will stop once all the nodes have been popped out. So how do I add into the queue and remove from the queue? So if you have to add something into the queue, that addition will happen from the ending. So add last. And if you have to remove something from the beginning, so we can call remove first method. So I can say okay, the node at the front of the queue. So that is int node. This is going to be queue dot remove first. All right, now what can I do? I can say okay, for this node, so node that I've removed from the queue is 0, right? So I need to traverse what are the neighbors of 0. So 0's neighbors are there in adjacency list, so they are 1 and 2. So what I need to do, I need to traverse on these neighbors. If the neighbors are not visited, I will mark them as visited and I will push them into the queue. So this is what I do. So I can say okay, for every neighbor. Okay, so to get the neighbors, what we can do, we can use iterator. I can create a iterator of the type integer and call it something like iterate it, and now I can say give me the neighbors of this particular node. So if you know, then this is the adjacency list I. So I want to iterate on this adjacency list of the node. So I can say, okay, while it dot has next, that means the next node is present. Basically, it is a way to iterate on the adjacency list. Sorry, you have to call a method called list iterator because we are iterating on the linked list. So zeros neighbors are 1 and 2, right? So these are stored in a list, which was a list object. So adjacency list of node is a list. We have to get the iterator using this method, list iterator. So it will iterate over these nodes until the list is not finished. It will go over these neighbors. Now I want to get the node, right? So how do I get the node? I can say, okay, the neighboring node is nothing but it dot next. That is the neighboring node. And now what I need to do, if it is not visited, if not visited neighbor, what do I need to do? I need to mark it as visited. I can say visited of neighbor, this is equal to true, and I need to add it into the queue. So I can say queue dot add last, and the item is neighbor. We are iterating over all the neighbors, and if the neighbor is not visited, we simply mark it as visited and we push it into the. So I hope this should suffice. And one more thing we can do in the while loop is we can print out the node. We can see what output do we really get. So I can say sout node. Now let us test our algorithm on the graph I have already constructed. So let me show you. In graph main I will go, and this is the graph, same as this graph, and now we are going to run BFS function on it. So I can say g dot BFS. Let's say the source node is 0. So let's go and run this code and see what output do we get. We should get all the nodes from 0 to 6 because we are doing a graph traversal. Let's see the output. Okay, we got an error, index 6 out of bounds for an array of length 4. Okay, so here we have to give, we have 7 nodes actually. Input needs to be fixed. Okay, so this is our adjacency list, and we are getting 0, 1, 4, 3, 6, 5. So we are getting all the nodes. That means the graph traversal is correct. Now the exact output will also depend upon the way you have stored these nodes. Okay, so you said, okay, zero's neighbors are 1 and 2. After 0 it will print 1 and then 2. But if you say in my adjacency list I will store 2 and 1 first, that means I will add this edge before this edge. Then the output will be 0, 2, 1 and so on. So right now our goal was to visit all the nodes which can be reached from node 0. So we are getting 0, 1, 2, 4, 3, 6 and 5. That means this output is correct. We are able to reach all the 7 nodes including 0. Now let us discuss one application of finding the shortest path from the source node to all other nodes. Okay, so what we are going to do, we are going to do shortest path from source to all other nodes in a undirected graph, in a unweighted graph. Unweighted graph. So this graph is an example of an unweighted graph. So graph can be directed or undirected, but it must be an unweighted graph for the BFS algorithm to work for finding the shortest path. Right? So we are going to talk about BFS shortest path algorithm. So the algorithm is very simple and it is very similar to just doing BFS. So let us try to visualize what we are doing in BFS. We are starting from node 0 and we can mark the distance of 0 as 0. And from 0 we are visiting the nodes 1 and 2. Since we are visiting a node for the first time, we will be updating their distance and we will be saying this distance is 1 and this distance is also 1 because we are coming from 0 and 0's distance is 0. Next, in the queue what you have done, you have said okay 0 is there, then you pushed 1, then you pushed 2 and so on, right? Now next item you will pick is 1 and you will update the neighbors of 1. Neighbors of 1 is, let's say, 4, and 0. 0 is already visited, so you will not go there. So you will say, okay, since I'm visiting 4 via 1, this distance must be 2. So distance of 4, I can say distance of the neighbor is 1 more than the distance of the parent. So parent is 1. Okay. So distance of parent. Parent node is 1, child node is 4, or the neighbor node is 4. 4's distance is 1 more than the parent. So I will visit 4 and I will push 4 into the queue. So next I will remove 2. So 2's neighbors are 0, already visited. 3 is not visited. So I can visit 3 and I can say, okay, this distance is going to be 2. So I will push 3 into the queue, and 2's neighbors is also 4. But 4 is already visited, so we will not update it. So it is not possible that you are reaching a node later which is already visited and the distance will get minimum. It's not possible in case of a unweighted graph. If it would have been weighted graph, this could have been possible, right? Now 4 is already visited, and since you are reaching from 2 again, node is already visited, so this distance will be either greater or equal to 2. So it is, we will not update it, so we will not do anything at 4. So 2 is done, 2 has done its work. Next we will pop out 4, and 4 can now update its children. So 4 children are 6, so this distance is 3, so you push 6, and 4 can also update 5, so this distance is also, you can push 5. Next you can pop out 3. Now 3 again, it will try to visit 6, but 6 is already visited, so hence you don't do any work. Then you try to pop out 6, so you can remove 6 easily, but there are no nodes, no neighbors of 6 which are not visited. Then you pop out 5, there are no neighbors of 5 which are not visited. So if you look at these values, you will find that these are the shortest distances from 0 to all these nodes. These are the shortest distances from 0 to all these nodes. So that means distance of 0 is 0, distance of 1 is 1, distance of 2 is 1, distance of 3 is 2, distance of 4 is 2, distance of 5 it is 3, and distance of 6 it is 3. So one observation we can make out from here is that BFS visits nodes in increasing order of their distance from the source node. This distance was 0. These two distances were 1. These two distances were 2. And these two distances were 3. Right? So this is an observation, right? So when I said you can get any ordering, so that means between these distances the ordering can change. So BFS might produce an output like 0 to 1. It might produce 4 3, it might produce 3 4. 5 6 might get 5 6 or 6 5, right? So different orders, but the distances of these nodes will be in increasing order from the source node. So that is how we can find shortest path from source to all other nodes in a unweighted graph by simply using the BFS. In the next part, we'll show you the code changes that we need to do for this algorithm. So it is very simple. Take a moment, pause the video, and think what changes you will make into the code. Alright, so let us discuss the code changes. So now, apart from the visited array, what you need to do, you need to maintain a distance array. The distance of each node from the source node. So you can say, okay, I need a distance array which is of size v, and in the beginning you can say distance of source. You can update that distance of source as 0, and rest is very simple. As you are visiting more and more nodes, you need to update the distance. So you can say, okay, I'm going to visit the neighboring node. So when I'm visiting this neighboring node, I can say distance of this neighboring node is 1 more than the distance of the node that is parent of this node. So that node is nothing but this node. So this node is distance of node. So that's it. Now what we can do in the same function, maybe we can either return the distance array or we can just print the distance array. So here I can say, let's just iterate over the distance array for I equal to 0, I less than v, I plus plus. I can show the node which is going to be I, followed by the distance which is distance of I. So let's go and run this code. and we should see we're getting node 0 at distance 0, 1 at 1, 2 at 1, 3 at 2, 4 at 2, 5 and 6 they are at distance 3. This is how easy it is to make changes in the code. And now we have made shortest path algorithm using BFS. Now some of you might be wondering that okay, we have figured out the shortest path, but we have only figured out the distance actually. What if I actually want to figure out the exact path from, let's say, 0 to some node 5, right? Maybe I want to find out what is the shortest path. Should I go like this, or should I go like this, or should I go like this? What will be the shortest path from source to destination in a unweighted graph? So again, this thing is very simple. So what we were doing BFS. 0 was visiting 1 and 2, 1 was visiting 4, 2 was visiting 3, and 3 was visiting 6. No, I think it was like this. 4 was visiting 5 and 6, and then uh, 3, something like this we did, right? So now, again, if you want to find out the shortest path to reach 5, you will know that okay, 5 was visited from 4, 4 was visited from 1, and 1 was visited from 0, right? What you can get, you can actually store the parent. So you can store parent of 5 is 4, parent of 4 is 1, parent of 1 is 0, and parent of 0 is, let's say, 0 or minus 1, anything you can put. What you can do, you can store these parents for every node, and then you can do trace back. You can say okay, I'll start from 5, and okay, from where I should go. So this is my destination node. So is the parent of 5. How do we arrive at 5? We came from 4, so I can go to this node. Okay, how do I came at 4? I came from 1, so I can go to this node. How do I came at 0? I will go to 0. Okay, how do I came at 1? I came from 0, so I go to 0. Who is the parent of 0? Minus 1. That means we have finished the entire path. In this way, you will be able to store 5, 4, 1, 0 in an array or in an array list. So this way, you can also print the shortest path from the source node to the destination node. The only changes in the code you need to make is you need to create a parent array, and when you're visiting from a node to a neighboring node, so you can say okay, parent of neighbor will be equal to node, something like this. And then you can simply put a while loop at the end. Once all the nodes have been updated, your BFS has been done, you can say okay, while I don't get the source node, let me travel back from the destination node. So you will travel this way, and you will eventually reach the source node. So this is something you have to try, you have to figure out, you have to make the required code changes in the algorithm that we have discussed. Now we will discuss one application of BFS in solving a problem. So we are given a snakes and ladders board which looks like this, and what we need to do is we need to find out the minimum number of moves that are required to go from source, which is from cell 1, to destination, which is cell number 36. So first of all, we need to decide whether it is a graph problem. So if you look carefully, you can analyze that we can clearly see there are 36 vertices. There are 36 nodes where you can go. So clearly we see vertices. But how do we decide the edges, right? So basically the question says there is a regular dice. So on your dice, you can throw any number of your choice from 1, 2, 3, 4, 5, 6, right? So the rules of the board are very simple. Whenever there is a ladder, you can climb that ladder. But whenever there is a snake, you will be cut by the snake and you will reach the tail of the snake. So you can cut down from head of the snake and you can reach the tail, this position, right? So basically, like in any snakes and ladders game, you have snakes which can cut you down and bring you down, and there are ladders which you can climb and move to the top. The question is how many minimum number of dice moves will be required to reach this destination. So you can assume there is only one player, it's not a two-player game. So the question is only about finding the minimum number of dice moves. We need to think carefully what kind of graph it is. If you analyze carefully, you will analyze that if we look at the dice moves, so at 1 you can throw a 1, that means you can reach 2, but at 2 there is a ladder, that means you will reach 15. So if I talk about this edge, there is an edge from 1 to 15 in this graph. Then if at 1, if you throw a dice 2, you can reach 3. There is an edge from 1 to 3 also. If you throw a 3 on dice, you can reach 4. That means there is a edge to 4 as well. And all of these edges are directed edges. And then if you throw a 4, you will reach 5, but on 5 there is a ladder. So that means the edge is from 1 to 7, right? And if you throw 5, you can reach 6. So that means there is an edge from 1 to 6 also, right? Now, if you throw 6, you can also reach 7. That means it is the same edge. We will not count that edge again. Again, starting from 2. So 2, there is a letter, so we do not need to do anything. Then you go at 3. So from 3, again, there are edges. So there is an edge from 3 to 4. If you see carefully, from 3, you can go to 4 and so on. From 3, you can go to 7 also. From 3 to 7, there is an edge and so on. That means how many edges I have. So I have approximately 6 edges starting from each vertex, from approximately 6 edges from each vertex. Okay, so if the vertex is v, I can go to v plus 1, I can go to v plus 2, I can go to v plus 3, v plus 4, v plus 5. This would have been the case if there was no snake and no ladder. But now what is happening is, suppose I go to v plus 1. Here there is a starting point of the ladder. So that means I will reach at some other position. So that means there might be a factor which will add up or which will be subtracted, and that factor will come from if there is a ladder at that position or if there is a snake at that position, right? That is what I'm saying, that it is an example of a directed graph. It is an example. Is it a weighted graph? The answer is no. It is an example of unweighted graph. That means all edges are equal, because the cost to cover any edge is dice throw. So it does not really depend what number you throw on the die. Each move is counted as one throw, right? So if you analyze carefully, you will see it becomes an example of a directed unweighted graph. And if it is unweighted graph, we can use the BFS shortest path algorithm to find out how do I reach this node, right? So in this case, if I analyze little more carefully, I will see from 1 I can go to 15. From 15 I can throw 3 and I can reach 18. 18, there is a ladder, I can reach 29. In order to reach 29, I just need 2 moves. Then I can throw 1 to reach 30, and then I can throw 6 to reach 36. So I guess in 4 moves I can easily finish this game. So I hope the problem statement is clear. Now it's your turn to figure out how do we construct such a graph, take input such a graph. So regarding input, you will be given the number of vertices, the number of snakes, the number of ladders, as well as the position of the ladder. For example, 2 to 15 there is a ladder, 5 to 7 there is a ladder, right? Similarly, positions of snakes will be given as pairs. 17 to 4 there is a pair, right? So take a moment to think, how do you input such kind of a graph and how do you make your BFS algorithm run on it. Alright, so let us discuss how we are going to build the algorithm. So I have written some boilerplate code, it's not the complete code. So I'm going to read some inputs. I'm going to ask enter the number of vertices, source and the destination. So I'm going to read these three things. After that, I will create a graph. Since I know the number of vertices, right? I can create a graph object or I can do it later on as well. That's fine. And I'm going to read the number of snakes and their positions. So in our scenario, we have 1, 2, 3, and 4 snakes. Number of snakes in my case are 4, and these are the positions of the snakes, 17 to 4. So I'm taking in this direction, head to tail. So that means 17 to 4, if there is a snake, you look carefully, 17 to 4, this is the snake. Similarly, I'm reading the letters in this direction. 5 to 7, there is a letter. So 5 to 7, there is a ladder. Now the question is, how do we handle this data? What should I do with this data? So first of all, I need to read this and I need to make sure that this data is used in my construction of the graph. Earlier we were creating a hard-coded graph, so we'll not do that thing here, right? So we'll create our own graph. So first thing is, here I'm just reading the number of snakes. I'm not reading what snakes I have. So I need to implement logic for that as well, right? This part I'm going to do it right now. So let's try to understand how we will actually create a graph. So we'll create a graph object C, and we will, of course, we'll try to add edges to it. Add edge. Now in edge, you need to know that from where the edge starts and where the edge ends. right? And it is a directed edge, so it's not a undirected graph. So I will set this third parameter as false. So now if I talk about vertex 1, so I told you from 1 I can go to, let's say vertex I can go to I plus 1, I can go to I plus 2, I plus 3, I plus 4, I plus 5, I plus 6, and plus something, right? This value could be 0, this value could be positive value, this could be negative value. What is this something going to be? It will depend upon whether there is a snake or a ladder starting from that position. For example, I plus 1. So at 2, I have a ladder which gives me, which actually takes me to 15, right? Which is actually taking me to 15. That means I'm getting a jump of 13, right? So for example, if I is 1, I take a move of 1, I reach 2, and 2, there is a ladder which is giving me a jump of 15 minus 2, right? So basically there is a ladder, so the delta that is given by the ladder, right? So if I go to, let's say, I plus 3, so there is no ladder here, so this delta will be 0, this delta will be 0. I plus 4, I reach 5, at 5 I actually reach 7, so this delta is 2. How do I compute this delta? This delta I have to compute and store it in an array. I have to compute and store it in an array. So that means in an edge, this becomes the starting point and this becomes the ending point of the edge. So this delta is very easy to compute. For example, you are given there is a ladder from 2 to 15. You can easily say, okay, I'm going to store it in some kind of array. Let's create a board array, right? So it's a 1D array of 36 positions, and in each position I'm going to store a delta. If someone says, okay, there is a ladder from 2 to 15, that means at the second position in this array I can store 15 minus 2, that is 13. So at the second index in this array I can store 13. So if there is a snake at let's say 32, which takes me at 30, let us assume this index is 32. So at 32 I get a delta of minus 2. So if I reach 32, effectively I reach 30. So 32 minus 2. So this is how I'm going to do it. Once all the edges have been inserted into the graph, I can easily run BFS on it. So let us try to insert all these edges into our graph. So what I'm going to do, I'm going to run a loop. Let's say for I equal to 0, I less than snakes, I plus plus. I can say, okay, snake has a head and snake has a tail. So I'm going to read these values. So I can say head equal to scanner dot next int, tail equal to scanner dot next int, and I'm also going to create a board array. So the board array can be created here. So int board, and this is equal to new int. How many? So I'm going to do v plus 1 because it is a 1 based indexing here. So I've created a board array. Oh, I have to move this code here because v is not input yet. So this board array will come here, or you can do it like this. That's fine, that's fine. Board array is now created. So now when I'm reading the snakes, right, so I have to update the board array. So I can say, okay, board of head. So in case of snake, the snake is going to bite from the head, right? So board of head will store a value that is equal to, because now it is giving you a decrement. So from 17 you are going at 4, right? Let's look once again. From 17 you are going at 4. So board of 17 should say that my value is nothing but 4 minus 17. So this value should be minus 13. So this is how it should be. So it should be equal to tail minus head. So tail is a small value, head is a large value. So this value needs to be negative. This will update the board array for snakes. Similarly, we need to update the board array for ladders, and we will utilize this array while constructing the graph. I will show you how. Make a similar loop. I have the ladders. Instead of snakes here, I will have ladders. Now the ladders are given in this fashion, bottom to top. So ladder also has a head and it also has a tail. So tail is, this number is smaller, this number is bigger. Tail minus head would be a positive number here. That is fine. So I think board array looks fine. So I can just display you the board array as well. So I can say s out arrays dot toString, and I can give the board array. Now I have this board array, I have these delta increments. Again, I need to figure out how do I insert all the edges. Now that thing is fairly simple. You need to go to every vertex and create the next 6 edges that will start from that vertex. For example, if I start from 5 or if I start from I can go to I plus 1 plus board of this position that you have reached. If you do 5 plus, let's say, some number 5 or 5 plus 4, you reach 9. But 9 is not the end position. You actually reach 27, right? I plus 2 plus board of this position. I plus 3 up to I plus 6. Basically, from ith node where I can go. So here I'm going to use the board array to decide where I can actually go. So this will be board of I plus 1, board of I plus 2, and so on. So let's see here as well. So let's create the graph now. So I have graph G. How many vertices I have? I have V vertices. So I'll just keep V plus 1 because it is 1 based. So we are also adding 0 here. This is equal to new graph. New graph of V plus 1 vertices. Alright. I have to add edges, right? So I can say okay, for int, let's say source which starts from, or let's say I'm going to add edge from I to something. So I to some j. Okay. So if I goes from, I can start from source which is 1, the smallest node. I can go till less than destination, that is my last node, I plus plus. So I'm going at every node. Then I can throw a dice at every node. I can throw 1, 2, 3, 4, 5, 6. So I can throw a dice. Dice can take a value 1. The maximum value dice can take is 6. And I can say dice plus plus. So what is the node at where I'm reaching? The jth node is I plus dice, right? But this is not final. I also have to add delta. So I can say okay, j equal to j plus board of j. So in this value, what I'm saying is from I you throw a die, you reach I plus dice. Now at this position, it is possible that there is a ladder. The ladder gives you a jump of 13. So you have to add this factor also that is stored in board of j. But if there is a snake that takes you down, so you have to decrement this value also. That addition subtraction is already handled in the board array. Now if j is less than equal to destination, that means I do not want to add any edge that goes out of the board. So I can say g dot add edge. So u is my I, v is my j, and it is not an undirected graph. So this value is going to be set to be. This completes the graph creation process. Now what we need to do, we need to run BFS algorithm on it. So as you know, we have already implemented the BFS algorithm. I'll just copy this code and tweak it a little bit so that we can do it for this particular problem. So I can say BFS dot s path. So in this case, I am getting source. I am also getting the destination. So if the user is interested in finding out minimum number of moves, so you do not need to print distance every node. You can simply return the distance of destination, and you can change the return type to integer. So this can be done. Now one thing might ask is, user might ask you to give the path also. So as I discussed with you, along with the visited array, you can create a parent array as well, and you can say okay, this is equal to new integer of v, and here you can say okay, for first node, that is my source node, the parent is, let's say, -1. So parent of source, this is -1, or you can set this is the source itself, something like this, so that you can know, right? Right now I'm just saying this is going to be -1, and whenever you visit a node, you can set the parent of neighbor is going to be the node. Now, as I told you, you can backtrack and you can find out the complete path as well. Let us discuss that thing as well. If you want to do the path printing, that is fairly simple. You can start from the destination node, let's say 36. Now 36 nodes from where I was visited. So maybe the parent of 36 is 30, right? So I can start from this node, reach this node, again ask the parent, go back, and so on. I can trace the path until I hit 1 or -1, something like that. So I can say fine, I take a temporary value which is destination, and I can say while parent of destination or while parent of temp is not equal to -1. What do I do? I say, okay, fine, I will print out the destination. I will print out the temporary node. So basically what I'm saying is the temporary node is this. Temporary node is 36. I will print it out and I will go here. This will become the new temporary node. But how do I update this temporary node? So fairly simple. Temp equal to parent of temp. At every node, I take it back to the parent. So this is basically going back to the previous node in the path how it was discovered. Then I'm saying return the distance of the destination. Now let us go and run this code. I think it should be fine. Yeah, it seems fine. So let us try to execute the code. So I've given the input, I've just combined the input and I'm giving it, but now I'm getting a error. Actually, I will tell you what is the error. So it is saying exception in thread main, index 38 out of bounds. So in main, this is the array. So this is going out of bounds. Why this is happening? Because if you add something to, let's say, node 35, you say, okay, I will take a jump of 3. You will actually reach 38. So actually I'm checking it here. So instead this check should be done here, right? So when I'm doing this value, when I'm computing this j, so I should do this thing here. If j is less than equal to destination, then I should do j equal to board of j. And again I should check if j is, you can do it here. Yeah, that is fine. So if j is now less than equal to destination, then you can actually add that edge. I think this would be okay. Or you can do two conditions here, right? So you need to check that, see what is happening is I added something here. I said, okay, 35 plus 2 or 35, or let's say 33 plus 2. Okay. And suppose there was a ladder here, right? It's not going to take you out. But what I'm checking is that when I'm adding this value board of j must be less than destination. And when I'm adding the edge, that edge must be less than destination. Let me run the code. Okay, so I think I commented out the shortest path. Let's rerun this code and it should be good to go now. So we do not need to print each and every node while traversal, right? One more attempt and then we should be good to go. We are doing BFS, we are printing the output of traversal, which we don't want. So let's paste the code and here we are getting, yes, this is the correct output. So we are getting the path and we are getting the shortest length, that is going to be 4. If I show you, this is the path that we are getting. From 1 we went to 15, 29, 30 and 36, and it took 4 number of moves. 4 moves were required to cover this. You can verify also. 1, 15, 29, 30, 36. From 1 we went to 15, then we went to 29, then we went to 30 and then we went to 36. Yes, these are the 4 moves that were used. So I really hope you understood this algorithm really well and the application of BFS we have seen through this problem. So that's all for this tutorial. If you like the video, please make sure you subscribe to our channel and I will see you in the next tutorial. Hello and welcome to this tutorial on graph traversals. So today we will be discussing about another graph traversal which is known as depth first search or DFS. But before we get started, make sure to check out free masterclasses on Scalar's event page to learn from best industry leading experts. Also, subscribe to our channel if you haven't already. Let's try to understand this algorithm called depth first search or sometimes called as depth first traversal. So it's an algorithm for traversing the graph or searching the graph. It can be used on tree. So on tree, the pre-ordered traversal that you have done, it's actually a depth first search. The algorithm starts at root node. So in case of graph, there is no root node. So you can arbitrarily, you can select any node as the root node and or you can have some specific node and you have to explore as far as possible along each branch before doing the backtracking. So we'll try to understand this through an example. And of course, this algorithm, since you are doing it recursively, uses extra memory, which is usually a stack. So if you're using a stack, in case of recursion, it will be created automatically. Even if you are doing this algorithm iteratively, you can maintain a stack like data structure and do the work, which is needed to keep track of nodes discovered so far along a specific branch, which helps in the backtracking in the graph. We'll understand this concept when we are running through the algorithm. And this DFS has many applications. Some of the applications I have listed down here. It is used in finding out connected components. You can also use BFS here. Basically, you want to look at what components of the graph they are connected. So for example, if this is a graph, this whole thing is one graph, it has two connected components. So you can do a traversal from this node, which will actually visit this whole component, and you can do a traversal from maybe this node, which will visit this whole component. So we'll do a separate tutorial on connected components. Topological sorting, it can be used. It is also used in finding out bridges in a graph. Cycle detection, it can be used. We'll look at cycle detection in this tutorial. Strongly connected components is a different concept which is used in directed graphs. So DFS again is used there, and it can be used to solve puzzles with only one solution, such as mazes. Maybe you want to find out a path in a maze, maybe there is only one solution, so you can easily use DFS along with backtracking to find out that particular path. It can be used in maze generation with the randomized DFS algorithm, and it can also be used in finding bi-connectivity in graphs. So let us try to understand the algorithm next. So DFS can also be used on a tree. So if you have this tree, so what this DFS will do, it will start from, let's say, root node. It will go in this direction, here, here, here. Then it will backtrack and it will enter into these branches. So it's just like a pre-ordered traversal that we have done on trees. But in case of graphs, the situation is little different. Why? Because graphs can contain a cycle. So we have to see what to do in case of a graph. Let us try to understand with the help of this graph how DFS will actually work. Let me draw the adjacency list as well. That will be input, and that is how the graph is actually stored. With 0 we have the neighbors which are 1 and 2. With 1 we have the neighbors 0 and 4. With 2 we have the neighbors 0, 3 and 4. With 3 we have the neighbors 2 and 6. With 4 we have the neighbors 1, 2 and 6. 5 we have only one neighbor, that is 4. With 6 we have two neighbors, that are 3 and 4. So this is how the adjacency list of the graph will look like. Now we need to understand how this DFS is actually going to work. So we are going to start from this node. It can be any node. So I'm going to take 0 as the starting node from the source node. And now since the graph can contain a cycle, I need to maintain a visited array. So I'm just drawing it here. So initially nothing is visited. So this is a visited array 0, 1, 2, 3, 4, 5, 6. So I need this much array, right? I'll call it visited. This will help me to ensure that I do not visit the same node again. If it is already visited, we'll just backtrack, we'll go back. So I start with 0, I said fine. I will mark this as visited, and since it's going to be recursive algorithm, so this node is in the stack. Now 0 can say, okay, what are my neighbors? Neighbor of 0 is 1. So it will pick this node, the first node. I will try to iterate, but first I picked 1, and I will make a DFS recursive call on 1. So I will go to this node. So I'll mark 1 as visited. So 1 is in the stack also. And now from 1, I can go to some neighbors, right? So 1's neighbors are 0. So 0 is already visited. So I'll not go here. I will, if I go, I just come back, right? So I say, okay, this, or I will not go. So this node is not visited. This 0 is already visited. So I will not make a call. But what about 4? 4 is visited. So I'm iterating on this list. So 4 is visited, right? So I make 4 is not visited. I make a call on 4. So I go and visit this node 4. So 4 is marked as visited, and 4 goes into the stack. So I think on the diagram you should also see a 0 here, right? Before 1 you have a 0, right? So this portion got little cropped out from the screen. So 0, 1, 4. This is how the stack looks like at the moment. At 4, I again do the same work. I look at what are the neighbors of 4. The neighbor of 4 is 1, which is visited. So don't do any work. The neighbor is 2, which is not yet visited. Now what 4 will do? 4 will visit 2. I'll go and visit this node. So 2 is visited and 2 is now part of the stack. Now at 2, I look at what are the neighbors. The neighbor is 0, which is visited. The neighbor is 3, which is not yet visited. So I go to 3, this node. So I mark this 3 as visited and I come to 3. So what are neighbors of 3? So it is 2 and 6. So 2 is visited, I don't do any work. 6 is not visited. So I go and visit 6. I go here. So 6 is marked as visited. So 3 is in the stack, 6 is in the stack. Right? Now at 6, I look at the neighbors. The neighbors is 3, which is visited, don't do any work. Another neighbor is 4, which is also visited. So don't do any work. Now what I can do? So 6 is already visited and 6 does not have a neighbor which is not yet visited. Right? So what you will do? You will go back. This is important. So this is backtracking. So you come back at 3. So from 6, you are now coming back at 3. So 6 is popped from the stack. Now at 3, you look at, I was running a loop. I was trying to traverse the neighbors and I already went and explored 6. So this is over. So from 3, I cannot go anywhere else. This list is over. So I will just go back. I will backtrack. I will come back at 2. So at 2, I see, okay, I went to 3. 3 is visited. Can I go to 4? 4 is also visited. So I cannot go to 4. So 2's neighbor have been visited. So I can say, okay, let's just go back from 2. I go back to the previous node. So before 2, I came from 4. So I come back at 4. So this is backtracking. Now at 4, I can say, okay, I went to 2. So 2 is visited. What about 6? Oh, sorry, what about 5? So this neighbor is 5 actually. 4 has a neighbor that is 5. 4 has neighbors 1, 2, 6 and 5. 5 and 6 actually. 4 neighbors it has. 1, 2, 3, 4. Yeah, 4 has 4 neighbors. So it will look at 5. Can I visit 5? The answer is yes, I can visit 5. So 4 will make a call at 5. And 5 will say, okay, I am visited now. So if I talk about the order, right? So it was like 0, 1, 2, 3, 6, and then, 0, 1, 0, 1, 4, 2, 3. 0, 1, 4, 2, 3, 6. And now you are actually visiting 5, right? You're now visiting 5. From 6, you come back 3, you come back to 2, come back to 4. And now 4 will say, okay, 4 has a neighbor that is 5. It is not yet visited. It will go and visit it. And 5 will say, okay, I can only go to 4, but 4 is visited. Hence, I will go back. So it will simply return. I go back to 4. Now 4 says, okay, 5 is visited. What about 6? 6 is also visited. 6 is not visited by 4, but it is visited by 3. So it will not go to 6 also. Now 4 says, okay, all my neighbors have been done. I will go back. It will come back at now 1, right? So here after 4, you went to 5. 5 is over. 4 is over. Now you come back at 1. 1 says, okay, all my neighbors have been visited now. I will just pop. I will come back at 0. Now in the stack, you are in this function 0. 0 says fine, all my neighbors. 1 is visited. Now 0 looks at 2. 2 is also marked visited in this array. So it says, okay, my list is also finished. So I'll just go back. So this is also popped off from the call stack. This is how the DFS algorithm works. And given this adjacency list, this will be the output that we will get. So the idea was to traverse all the nodes, and this is what we will get by traversing all the nodes. Okay, so I hope you understood the algorithm. Fairly simple. If the graph has multiple different components, then we will see that you need to initiate DFS from one node in each component. Okay, so this is something easy that can be done later on, but first of all we'll focus on this simple DFS algorithm where we are assuming there is only one component. Okay, so we are assuming one component in the graph as of now. So let us code this algorithm next. Let us look at the implementation of DFS in Java. So I already have the graph class which is implemented in the previous tutorials. So in this, I'm going to add a DFS method, and this is going to accept the source node from where I'm going to start the DFS. So I'm assuming there is a single component in the graph. So what I need to do? So firstly, I need to build a visited array. That is the data structure we will be needed. So we can keep things simple. We can create a Boolean visited array, and this is going to be of size v. That is the number of vertices in the graph. So initially everything will be set to false, and in Java by default a Boolean array is false. Now I actually want to do this traversal recursively. So I cannot make this as a recursive function because I cannot create this array again and again in the recursive function. So what I want this array to be shared across all the function calls that I'm making. So for that is why I need to create another function which is going to help this DFS. I can call that as DFS helper, and here I'm going to get the source node or the node, the current node where I am, and the Boolean visited array. So this array will be passed and it will be shared across all the function calls, right? So I can simply make call to DFS helper, and I can give source node and the visited array as input to this function. Right now here what I need to do, as soon as I come to a node, the first thing I will do is I will mark that node as visited. So I can say okay, I can print out that node, that is fine, and I can say visited of that node, this is equal to true, that yes, I have visited this node. Let us take a small example. Let's say I have 1 2 3 and 4 and 5. Let's say this is the graph. So if I start from this node, so I will mark this as visited, and now I will look at neighbors of 1. So 1's neighbors will be, let's say, 2 and 4. So I'll iterate on this list and I will go to the neighbor which is not yet visited. So right now 2 is not visited, so I'll make a call to 2. Okay, so how do I do it? To iterate on this list, we need to create a list iterator. I think this part was not visible, so I'll just hide myself. What I'm saying is that 1 has neighbors 2 and 4, so I'll make a call at 2 first. So how do I get that? For that I need to create a list iterator first. So I can say fine, let us create a iterator of the type integer, let's call it it, which is the iterator to iterate on this list. So I can say okay, adjacency list of this node, which is, let's say, 0 source in my case, dot list iterator. So using this iterator we can easily iterate. So while I have items in this list, while it dot as next, what to do? I can say okay, give me the neighboring node. So the neighboring node, this is given by it dot next. So I will now check, is 2 not visited? Yes, 2 is not visited. So how do I check? I check from the array. So 2 is not visited neighbor. Then what to do? I have to make a recursive call. So I can make a call to DFS helper, give it the node is neighbor, and give it the visited array. Right? So I'll show you what's going to happen in this scenario. So I have this, let's say 1 2 3 4 5. So generally in the code the indexing is assumed to be 0 based, but in the example I took it 1 based, but hopefully you will understand that part. So I check 1 is connected with 2 and 4. So 2 is not yet visited. So 1 is visited. So as soon as I come to 1, I mark 1 as visited. Then I iterate over the neighbors of 1. I check 2 is not visited. So I make a function call on 2. So 2 is now visited. Now I look at neighbors of 2. So 2 has neighbors which is 1 and 3. So out of this, 1 is already visited. So I don't do any work. So I'll make a call at 3. So as soon as I come to 3, 3 is visited. And 3 has neighbors again 2 and 4. So 3 looks at okay, 2 is visited, so I'll make a call at 4. At 4 I have again neighbors which are 1 and 5. So 4 says okay, 1 is visited, don't do any work, make a call at 5. So 4 visits 5. So 5 is now visited. Now 5 has only one neighbor 4 which is visited. So this loop will not run for 5 because it will iterate on 4 and 4 is already visited. So this if will not execute, and while will not do any work. So you will simply return, right? So from here we will come back. So you come back here, right? Now at 4 you see 5 is done. So list of 4 is also finished. So this loop is over. 4 goes back to 3. So 3 says, okay, I can go to 4. This is also done. So 3's loop is also over. You go back at 2. So at 2, you have gone to 3. That's also done. Now suppose there was a node 6 here, right? So what will happen now? 2 will say, okay, yes, I can go to 6. So 2 will go to 6 and 6 will get visited and you will come back, right? And of course, these nodes are also marked visited. This loop is also now over. Now at 2, you will say, okay, my list is done. I will go back. It will go back here. Now 1 will look at, okay, can I go to 4? But 4 is already visited. Hence, you do not go. You do not make a call at 4. So this edge is not considered. And at 1, you can say, okay, this list is done because 4 is also visited. And hence, I go back. This is how it will go back into the main. So in this case, the output would look like 1, 2, 3, 4, 5, and then you have gone to 6 as well, right? This is how the DFS is going to get performed using this code. Now let us test our code. Does it work fine or does it work as expected? So you have understood DFS on graphs. Next thing we will learn is how do we do cycle detection on graphs. Basically, we will do this algorithm of cycle detection on two types of graphs. One is on undirected graph, which is given here, and secondly we will do it on directed graphs in which the algorithm will change a little bit. This graph is an example of a undirected graph. So now how do I detect a cycle in this? So I can use BFS or DFS, right? So if you remember, the fundamental difference between a tree and a graph is that a tree is always not containing a cycle. Tree does not contain a cycle, but every tree is also a graph. Basically, if you have a cycle in a tree, it becomes a graph, right? And every tree is also a graph. So if I give you an example, let's say this is node A, it is connected with B, and it is also connected with C. So right now it is a tree, right? And it is also a graph. But if I add this edge, it definitely becomes a graph, right? It is not a tree now because it contains a cycle, right? So now what is the significance of cycle, or how do we detect a cycle? So it is pretty easy. Let's say I start traversing this using any algorithm, let's say BFS or DFS. Let's say I start with A and I make a DFS call on its child, that is B. At B, I make a DFS call on its child C, and C will now look at its neighbors. So it will see, okay, I discovered a neighbor, right? Now C has two neighbors. So one of the neighbor is, let's say, B, right? So if C looks at B, right? B is already visited. But is it really a cycle? The answer is no. I cannot say that this edge is going to create a cycle. The answer is no, right? Let's say there is one more edge from C to D. C makes a call at D and it visits D. Is this edge causing a cycle? Basically, the answer is again no, right? So what is the difference between this edge, right? So basically, before visiting D, D was undiscovered. D was not visited, but B was discovered. B was discovered. Now suppose I create one more edge, which is this edge, right? So if I now C makes a DFS call on, let's say, A, right? But as soon as I make this call, I see, okay, I'm landing at a node which is visited, and I can say it is a cycle, right? It is a cycle, right? So basically what I'm trying to say is that B was also visited, D was not visited. So here we are sure there is no cycle. But here the answer is no, because B was discovered, but it was parent of C. It was parent of C, right? It was parent of C. Whereas from C, when you go to A was already visited and A was not the parent of C. A was not the parent of C in the DFS call. Right? So this is the condition, that if we encounter a node which is already visited and it is not the parent of the current node, then we can definitely say yes, there is a cycle that is present, right? So let me dry run this algorithm on this graph. So let us create a adjacency list. So 0 is connected with, let's say, 1 and 2. 1 is connected with 0 and 4. 2 is connected with 0, 3 and 4. Then 3 is connected with 2 and 6. Then 4 is connected with 1, 2 and 6. Then 5 is connected with just 4 and 6 is connected with 3 and 5, right? Now suppose I start doing a DFS from node 0 and I want to check if there is a cycle or not. So I start from this node 0. I said okay, go and make a call at its neighbor. So 1 is the neighbor, it is not visited. So right now my goal is to iterate on this, but I make a DFS call on the first node that is not visited. So 1 is not visited, I go here. Now at 1, I look at the neighbors. The neighbor is 0. But if you look at 0, 0 is already visited. 0 is visited. But 0 is also the parent of 1. So hence we have to skip this node. We will not do anything at 0. What about 4? 4 is not yet visited. So I go and make a DFS call at 4, right? Now we come at 4. 4 is now marked as visited. 1 is visited. 0 is visited. 4's neighbor is 1. So I will not do any work. Like C's neighbor is B. B is visited. 1 is visited, but 1 is parent. So we will skip it. What about 2? 2 is not yet visited. So I can go at this node and I can mark it as visited, right? Now look at 2. Now 2 has a neighbor that is 0. Now this is an interesting case. Okay. So 2 has a neighbor that is 0. So I will draw this edge separately. I'm going to mark this edge in red. So 2 says, can I go to 0? Now what is the condition at 0? 0 is already visited, right? And 0 is not the parent of 2, right? So basically you are hitting this edge. We will call this edge as a kind of a back edge, right? So it is taking us back in the same path from where we started or to one of the ancestor nodes, okay? So it is an edge from the current node to some ancestor node. Why ancestor? Because if you look at the path that we have traced is 0, 1, 4, 2, and then from 2 we are going back. We are going at 0. This is like a back edge, right? Now, as soon as I get this edge, it will be the terminating case, right? So at this point I can directly say without looking at the rest of the graph, yes, there is a cycle. So this is going to return true. Okay, so I'm going to say okay, I'm going to return a true from this node 2. So this true will be told back to 4. Okay, so 2 will say okay that yes, I found a cycle. Okay, so what 4 would have said that okay, I do not see a cycle in my, I am not seeing the cycle as of now, but let me call a neighbor and check if it can discover a cycle. So 2 discovered a cycle, so that true is returned to 4. 4 will also return true, 1 will also return true, and 0 will also return true, right? Because it's going to be a stack based algorithm, so this true will be propagated back to the main in this manner, right? So there will be a base case, there will be a recursive case. So let us try to write the code and understand this algorithm in little more detail. So let us write the code for cycle detection. So I'm going to make a boolean method which is, let's say, detect cycle, and here I need to give some source node from where I want to start, right? Or you can take 0 as well, right? So we are assuming that the nodes are numbered from 0, and we can ignore this source, we can directly give 0 as well, right? So now since it's going to be a recursive function like DFS, right? So one thing we did in DFS was we maintained a visited array. So we also need to maintain a visited array that will tell whether a node has been visited or not. So boolean visited, this is equal to new boolean, and the size is, let's say, v, right? So by default this visited array is set to false in Java, so I'm not explicitly setting it. And here I can say okay, I'm going to create a helper method, detect cycle helper, and I'm going to give it a node, let's say 0, and I'm going to give it the visited array, right? So this method is just like a wrapper function because we need to create the visited array, and this needs to be shared across all function calls. So we are going to make a helper method boolean detect cycle helper. It's going to accept the node, and second thing it's going to accept is the boolean visited array. So now here we will return some true or false, right? So let's see how this is going to be. So first of all, when you're encountering a node for the first time, so definitely you should mark that node as visited. So visited of node, this is equal to true. Next thing you will do is you will iterate over the adjacency list of that node, and you will make recursive DFS calls, right? So let's see how we can do it. So just like before we have done here, right? So I'll show you. So you will create a iterator to iterate on that node, right? Or like in DFS, right? Something similar we will do, right? So I'll just copy this node code, and I'll show you what modifications you need to make in the DFS code, right? So here we go. So we have created an iterator to iterate over the adjacency list of the given node. And then what I'm saying, I'm finding out the neighbor, right? So if the neighbor is not visited, now here the call will be different. Okay. So if the neighbor is not visited, I will go and visit that neighbor, and I will also store the result what that neighbor is saying. For example, let's say 1 is connected with 2, 2 is connected with 3, 3 is connected with 4, and 4 is again, let's say, connected with 1, right? So I will make a call at 2, that is the neighbor. Now this 2 is supposed to return some result back to 1, right? So that result can be true or it can be false. So 2 might have called 3, 3 might have called 4, 4 might have called 1. Oh, and here it saw, yes, there is a cycle. So true, 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 that will get propagated back, right? So if the neighbor is not visited, definitely we have to go and check that, okay, yes, is there a cycle at that node or not? I can say, okay, Boolean, I can say um, cycle found, right? Something like this. So they did find a cycle in that part of the graph, right? So here I can make a call to detect cycle helper, and here I can give the node, which is going to be the neighbor, and I'm going to give the visited array, right? Now this is like a recursive case. You called some node, that node said, yes, I found the cycle. If the answer is true, if cycle found is true, you can directly return true from this point without iterating on the remaining adjacency list of the current node, right? And there is one more scenario that can happen outside this if, right? Outside this if, so it's like a recursive case I've written here. So this is like a recursive case. There can also be a base case, right? So base case would be that you are hitting a node which is already visited, right? So I can say else if visited of neighbor, this is true, right? This is true, right? And there is one more condition, right? So I'm basically saying something like this. 1 is connected with 2, 2 is connected with 3, 3 is connected with 4. And now you said, okay, I came to this node, I came to this node, I came to this node. From 4 to 1, there is an edge. So as soon as you discover this edge, that fine, I am going to a neighbor which is already visited, and this 1 is not the parent of 4. Okay, so 4's neighbor is also 3, but 3 is the parent of 4. So you cannot say about cycle at this node, okay, but you can say about cycle because of this edge. 4 is taking me to the 1 which is not the parent, right? So you can say the neighbor that we have discovered is not equal to parent of 4. But how do we get parent of 4? That is a question. Okay, so this is the neighbor, right? So that means, and this is the parent. So we want that this neighbor that we are discovering should not be same as parent, because 4's neighbor is also 3, right? If it is 3, then we cannot say anything, right? We have to skip this. But this neighbor, if it is not same as parent, then yes, definitely there is a cycle. But how do I find the parent of current node, right? So that is a question. This parent we will have to maintain in the function call by passing one more parameter, right? So parent, and here we have to, so when you discovered this neighbor, right? The parent of this neighbor is going to be the current node, right? So this will be node. So I'm setting the parent here. If neighbor is not equal to parent, then I can say return true, right? Since I'm using a else if condition here, right? So this else if will be only executed if the node is already visited, right? So if it is not visited, it will go here, but if it is visited, it will come here. So that means writing this part is optional. So I can just remove this and I can just simplify the condition to be only this. Neighbor is not equal to parent. I'm going to return true. But if I come outside the while loop, that means I could not detect any back edge, right? So this is actually the point where we are detecting the back edge, and this is actually the recursive case. This if condition is a recursive call, that's it, right? So this is kind of a base case that we found a back edge, right? Otherwise, if we could not find any back edge, we are going to return false from that node. So I think this function looks good to me. Now we have to give a parent here as well. So parent of the source node, we can just set it to -1, no parent, right? And let us dry run this code and let us also test the functionality first. So here in the main, I have this file. So I have created a graph. I have done the DFS, simple DFS works, but now I want to S out about the cycle detection. So if g dot detect cycle, you can just see out S out, yes, there is a cycle, else you can say S out, there is no cycle. Let's go and run this code. So let's see what output do we get. So it says yes, there is a cycle. So I'll show you, this is the same graph that we have in the figure. So yes, it contains a cycle. So let me dry run this code for you once again. So I'll do it on a smaller graph. Let's say the graph looks like this: 0, 1, 2, 3, 4, and let's say this is the edge, right? So you start from 0, so parent is -1. So you look at neighbors of 0, right? So you said, okay, visited of node, this is true. So this is marked as visited. Then you iterate over the neighbors. So neighbors of 0 are 1, 2, 1 and 3. First we will go to 1. 1 is not visited. So we make a recursive call and ask, did you find a cycle? So 1 is now marked as visited. And when I marked 1, so I said the parent of 1 as the node. So this was the node, this was the neighbor. So neighbor's parent is going to be the node. So parent is 0. So one's parent is marked as 0. And again, same story repeats. At 1, what do? I make a recursive call. So I ask neighbor of 1, right? Now 1 has two neighbors. One of the neighbor is 0. 0 is visited. But what happens here? Is this condition true? What is the neighbor? Neighbor of 1 is 0. What is parent of 1? That is also 0. So we do not execute this else if block. So we basically ignore this case. Okay, we do not do any work here. Then we look at the second neighbor. So 1 has neighbors that are 0 and 2, right? So nothing happens here. What about 2? So 2 is not visited. So we make a recursive call, right? So we go to this node, we make a recursive call. Now 2 is marked as visited. Parent of 2 is 1. Now 2 also has two neighbors. 2 has a neighbor that is 1 and it has a neighbor 3. So I do not, if I look at 1, 1 is already visited, right? So I come into this else if. Okay, if it is not visited, I go here, but if it is visited, I come here. So what is the neighbor of 2? That is 1. What is parent of 2? That is also 1. So this condition is also not true. So I do not do anything here. So nothing happens here. We talk about this edge, 2 to 3. So I go to 3. Now at 3, what happens? 3 has two neighbors, 0 and 4. So I go to 0. Is 0 visited? Yes, 0 is visited. So I do not go into this if block, I come into this else block. What is the neighbor, right? So what is now the neighbor of 3? So the neighbor of 3 that I'm considering here is, because of this edge, that is 0. What is the parent of 3? The parent of 3 is actually 2, right? So they are not equal. Yes, 0 and 2, they are not equal. That means yes, return true. So without looking at this part of the graph, 3 returns are true, right? Now 2 got to know, yes, there is a cycle found. So 2 also returns are true. It goes back. 1 also gets to know, yes, there is a cycle found. So as soon as it gets a true, it returns a true. 0 gets to know, oh, yes, there is a cycle, it returns a true back to the main. So this is how this algorithm is working, and I hope you understood it. Now we will talk about cycle detection in case of directed graph. So in case of directed graphs, not just the structure of the graph, but the direction of edges also decide whether there is a cycle or not. If you look at this example, the edges are like this, and if you start from A, you can go to B, you can go to C, but from C you are not able to go to A, right? And of course there is no loop present here, right? So hence there is no cycle. But if I change the direction of this, just this edge, I reverse it, right? I can go from A to B, B to C, and from C I can again go back to a node. I can go in a cycle. So hence, yes, there is a cycle, right? So now I will tell you, if you use the same algorithm which you used on undirected graphs, what is the problem you're going to face, right? It's not going to work in the same manner. So let me take up one more example. Let's say the graph is like this. Let's say A. From here we have B. Let's say C, D, E, F, and let's say this is connected like this. And let's say I have G, and it is connected with, let's say, C, right? Now suppose you start doing DFS from A, and you say if I hit a node which is already visited, I will say there is a cycle. This is the logic we did in the undirected graph. So let's say you started doing DFS, you started from A, you went to C, okay, from C you went to D, from D you went to E, from E you went to F, and from F you cannot go anywhere else. So you come back and you say, okay, no, there is no cycle. So you come back, you return false, right? And from E again you come back, D, you again come back at C, and again you come back at A, and from A you come back at B. Now you go to V, B is not visited, right? From B you go to G, and from G you go to C, and now you see that I am going to a node that is already visited, this edge, right? And it is C is not the parent of G. That means I'm going back in the path. But is it really a cycle? My question to you is it really a cycle? The answer is no. If you start traveling from A, you can come to C, and you cannot get stuck into cycle. From C you can go to E, right? So this is not a cycle. Or you can go to D, right? Go this way. So this is again a case of non-cyclic graph, right? But if you run the previous algorithm that we executed on a directed graph, it is going to say yes, there is a cycle, because from G you discovered a node which is already visited, right? Hence we need to fix this algorithm, right? So we need to fix the algorithm for directed graph, for directed. Now the question is, how do we fix it, right? So thing is, we need to again detect back edges correctly, right? So from G to C, this is not a back edge, right? I will tell you what is a back edge in case of a directed graph. So back edge is a edge that takes you back to from one of the node to some ancestor node in the same path, right? From the current node to some ancestor, right? Ancestor. So let us take another example inspired from this graph only. Let's say I have A, I have C, I have F, I have D, and I have E, and I have F. Then I have, let's say, B, then I have, let's say, G, and then I'm pointing to, let's say, C. And let me add one more edge in this graph. So this graph, this edge maybe looks like this. Let's say the edge is like this. Do you see a cycle here? The answer is yes, there is a cycle, right? Or let me add two more nodes, right? Let me add a node, let's say H, and let me add a node. That's it. Let's say one more node I have added. Now in this part of the graph, there is no cycle. But yes, in this part of the graph, there is a cycle, because you can revolve in this path again and again, right? So let us try to see what is a back edge in this scenario, right? So let's say we started doing DFS from A, I went to C, from C I went to D, I went to E, from E I went to F, from F I cannot go anywhere, so I will just come back, right? So what is the state of the call stack? The call stack has A, it has C, it has D, it has E, it has F. Now if F says I cannot go anywhere, so I'm just going to return false. So false is propagated back. Then E says, okay, I cannot go anywhere else, I will come back. D says I cannot go anywhere else, I'll come back. C says I cannot go anywhere else, I come back to A. Now A says, okay, let us go to B. So B goes into the stack. B says, let's go to G. G goes into the stack. Now from G, I can go to C. C is already visited. But is it a back edge? The answer is still no, right? Because in the current path, right? So if G is giving me a edge that is pointing back to one of the ancestor in this call stack, only then it will form a cycle, right? So the answer still here is no. So I will not take this edge. So can I go anywhere else? Okay. So basically, what is the condition I'm going to check here? So when I'm checking G to C, C is visited. C is visited, but C is not in the stack. C is not in the stack. That means I came to G via path which does not include C. Okay, it is not in the stack. That is the important condition, right? Now G can say, okay, let me go to H. H is not visited, fine. H goes into the stack. Now H says I can go to A. So what happens here? We are going to a node that is visited, and that is also in the current path, right? That means from H I can go to A. From A, if you A again, you can go to H, A, B, G, H. So that means these nodes will form a cycle, A, B, G, H, right? What is the condition to detect a back edge? So I will say, okay, in this DFS traversal, this edge from H to A, this is forming a back edge, right? Because I'm going back to one of the ancestor nodes, right? So the condition is from the current node to some ancestor which is in the stack. We have to check two things. We have to check that this node A is visited and A is also present in the stack. A is in the stack, right? So if both of the conditions are met, we can say yes, there is a cycle, and recursively H will propagate back. So H knows yes, there is a cycle. G knows yes, there is a cycle. B says yes, there is a cycle, and A also tells back yes, there is a cycle. So this is propagated back. There is a cycle. So again, this can be implemented recursively, but how do you check whether A is in the stack, right? So we cannot directly look at the recursive stack. So what you have to do is you have to maintain another data structure. Either you can maintain a hash map or you can simply maintain a array, right? So whenever you are hitting a node, you mark it as visited. Okay, so when I hit A, so these nodes will remain visited, right? But when you're going back, okay, when the nodes are getting popped from the stack, you can remove that node from the stack array also, right? So I can simply create an array called in stack. So if you're visiting a node, next you can mark that yes, it is visited. But when you're going back, you're backtracking. For example, when you went back from C, you can say yes, this node is not in the stack, right? So you have to maintain two Boolean arrays, one for visited, one for stack. While backtracking, you will unmark from the stack array, right? So I'll write the code first, then we will do the dry run. But I hope you understood the concept that here just being visited is not sufficient. We also have to check whether the node is in the stack or not, right? So this is the main tweak that we will use in this algorithm. Hello everyone, in today's tutorial we are going to build a flood fill algorithm which is commonly used in the paint buckets fill method in designing tools like Photoshop, Paint and others. We are going to look at how do we implement this algorithm using the concept of graph, and we will use BFS and DFS to implement this algorithm recursively and iteratively. But before we get started, make sure you check out free masterclasses on Scalar's event page to learn from some of the best industry experts. Also, subscribe to our channel if you haven't already. Let's begin with the tutorial. So let us understand the problem statement first. So in all these designing tools like Photoshop, Paint, what do you have? You have an image and you have to manipulate pixels of an image by filling some color. So what we have to do, we are given an image. So in general, an image is represented as a grid of pixels. It's a 2D grid of pixels where each pixel represents a color, right? So that is a separate discussion, that each pixel is made up of three integers, a component of red, green and blue. So effectively at the memory level, image is a 3D thing. But if you look at image as a grid of pixels, it is actually a two-dimensional data structure. For the sake of simplicity, we will represent each color by a single integer. But in actual, it's going to be a component of RGB, right? So that actually makes each image a 3D matrix. But for now, we are assuming that each color is an integer and we are representing this image as a 2D matrix. So image is represented by a m cross n matrix, where image ij represents the pixel value of the image. So 1 represents a color, 0 represents another color, and so on. You're given three integers, SR, SC and color. You should perform a flood fill on the image starting from the pixel at the image SRSC. Basically, we are given, okay, you have to drop the paint bucket tool at this particular some coordinate, okay, some coordinate SRSC it is given, and it should do a flood fill. That means the color should spread in the neighboring regions which are having the same color, right? So for example, if I drop a color 2 here, it will spread in the neighboring regions and it will make these pixels as 2, right? So this is not affected because it's about also about the connectivity, how the neighboring pixels are considered. Is it a 4-directional connectivity or is it a 8-directional connectivity? So let us understand the second part of the problem statement. To perform a flood fill, consider the starting pixel plus any pixels connected in 4 directions. So basically, if this is a pixel, the neighboring pixels are top, right, left and down. The diagonal pixels are not considered as neighboring pixels. So connected to the 4 directionally to the starting pixel of the same color plus any pixels connected 4 directionally to those pixels also with the same color. Okay, if there is a pixel with color 3 here, so it will not change its color because it represents a different color, right? And so on. Replace the color of all the A4 mentioned pixels with the color. So basically, if you drop the paint bucket here, now this has a neighboring pixel, this has a neighboring pixel, this which is of the same color, these pixels will change its color. Okay, so return the modified image after performing the flood fill, right? So to make the things little more clear, I have found a visualizer on the internet that I will show you. So in this visualizer, we will draw some shape and we will try to drop the color just like we do in paint or any other tool. So firstly, I'm going to draw some shape, and in order to draw the shape, maybe I'll choose a black color. So I have to click and I have to, maybe I'm just making some kind of a maybe apple or something, right? So let's say this is the shape I have created, right? And now I can just, what I can do, I can say, okay, I want to fill inside this shape. I will select a pixel, I will select a color. Let's say I will select the green color and I've selected the fill method. Now this is where the flood fill is going to come into picture. I'm going to maybe drop the color here, right? Now you can visualize this, all the white pixels, they are of the same color and all of them which are the neighbors, they are connected, right? If I drop a green color here, you can see this got filled. What exactly happened? It executed a DFS based algorithm. So let me show you how did it work. So I dropped the green color here. It said, okay, can I go to the left pixel because it was also white? So yes, it went and made it green, 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 green. So this way it went. Now from here, it cannot go right. So what it can do, it tried to explore, can I go to top? No. Can I go back? No. Can I go down? Yes, I can go down, right? Again, it cannot go right. So either it will go down or either it will go left. So it will happen like this. Okay, so the DFS will happen like this, and so on. And maybe then it will backtrack. It will come to this point. It will say, okay, can I go top? Yes, it can go to top. Can I go top? Yes, I can go to top. Now here I cannot go top. Maybe I can go right and so on, right? So this way, this entire grid will get filled. Basically, you need to decide a direction, right? So when you're making a function call, you will follow a specific order that, okay, I will make a call to the topmost pixel. If I can go there, I will go there. But if I cannot go there, maybe it is a black boundary. So I will not go there. I will come back and I will go right. So again, recursively, you will go right. Again, recursively, you will go right and so on. But at some point, you might come back from that branch because there is no further So here is a boundary. So you come back. Can I go down? Yes, I can go down. I can go down. I can fill the entire region, right? But at some point, it might happen that there is a boundary here and there are no more cells available to get filled. So you might backtrack, you might come back here. And now you might explore this direction or this direction, right? So you'll follow a certain order, but irrespective of the order that you follow, this flood fill will be able to fill the entire region, right? So if you want to try out one more example, we can do that. So I'll just reload the page. I will click on draw. So I will draw a complex shape this time in which we have, let's say, two components, right? So now if I leave maybe a little bit of space here, right? Okay, now if I say, okay, I want to fill, and now you can see in this region there is no way to come. So if I fill red color in this region, maybe I will drop it at this point. This part will get filled, and there is no way for the color to leak into this region because there is no connectivity, right? So the connectivity is a four-way connectivity. If it was a diagonal connectivity, the color will also leak into this region. The red color will come into this region, right? This is how the flood fill is going to be done. And now we will look at the implementation, understand the algorithm, and implement it using DFS. Let us try to implement the flood fill algorithm, and I will explain you the steps side by side. So I've created some boilerplate code and I have made the function call. So this is the method that I would like to finish. So I'm getting the image, I'm getting xy, which is, let's say, some current coordinate, and some current color, which is, let's say, the color at xy, and the new color that I want to fill. Maybe I want to fill these ones with fives, right? Maybe I want to put 5 here. So that is maybe the new color, right? Now let us try to see what's going to happen. Let us assume that we have just one row and we have 4 pixels. So let's say this is the black color, this is the boundary, and you start a flood fill from this particular cell, and you go into 4 directions. You go right, you go down, you go left, and you go top. So when you go right, since it is a DFS call, so it will recursively make calls on the next cell. So you make this as 5, you come here, you make this as 5, you go here, you make this as 5. Now you hit this cell. Now this is of a different color, right? Maybe this is a boundary. So what you have to do, if you hit a different colored cell, you have to go back, right? Now the next direction you explore is down, but going down, it is possible that you might have array here, right? So let's say we have more cells here. So you come down, you say, okay, this is white, I need to paint it. So you put a 5 here, and again you try to go right. So you go right here. You again, it is white, so you put it 5. Again, if you go right now, what you observe, you are going outside the grid. So if you hit a cell which is outside the grid, you have to immediately come back. So you will return, right? Next direction you explore is you go down. Again, it is outside the grid, so immediately you come back. Then left. So if you see left is already painted in 5. So it is of the or this color is same as the new color that you want to paint. So again you will come back, you will not go here. And now this direction is also explored. What about top? Can you go top? Top cell is again a boundary. So what do? Now you backtrack. So you can say, okay, I'm done at this cell, I cannot do anything further. So you come back to the previous cell, which is this. Now at this cell, you have explored the direction right. Can you go down? Again, it is outside, so you come back. But can you go left? Yes, I can go left. So you explore this direction. Again, can I go right? Right is already 5, so you do not go there. So can you go down outside the grid? You cannot go there. Can you go left? Yes, I can go left. So I make it 5. Again, can I go right? No, it's already 5. Can I go down? It is outside the grid, so you come back. Can I go left? Again, it is outside the grid. Can I go top? So it is already 5. So it is basically checking this 5. It is serving the purpose of visited, right? So we do not want to go to that cell. So you do not need to maintain a visited array separately because the color is 5. That means we have already painted this cell into new color. So you can just come back, right? Now again, at this point, what you will do, you will backtrack. So you will go back to this cell, You'll go back to the cell. From here, you will now go top, which is again 5. You will come back, and now you can see at this cell we have visited all directions. So I'll just backtrack here. Can I go top? Again it is 5, so you backtrack. Now at this cell also I have visited all directions, so I backtrack, I come here, I backtrack, I come here, and so on, right? So this is how the flood fill algorithm is essentially going to work, and it is going to fill the shape in which we are putting the color. Now let us implement the code along with the various conditions. So the first condition is going to be, if I'm going to go outside the grid, I can immediately come back. So outside the grid, what do? You have to return, right? So for that I need to know the number of rows and columns. The number of rows will be nothing but, you can say, image dot length, and number of columns will be image of 0 dot length. So length is not a function, it is a property of array, so we can fix it. So if you have image, right, so number of rows n will be the length of the image array, and number of columns will be equal to the number of the length of the 0th row or any row, right? So that is how I know the size of the array. What will be the condition? So if x is outside the grid, so if x is less than 0, that means my row number is less than 0, or x is greater than equal to the nth row, right? Or my column number is less than 0, or my column number is greater than equal to m. In this case, I do not need to do any work, and I can simply say return. Then what else? So if I encounter the boundary, so another condition would be, you encounter a cell of different color. So for example, you wanted to fill the cells which are 1, but from 1 you go to 2. So if you go to this cell, you do not need to change it, right? So that means the color if the color in the image at cell x comma y is not same as the current color, so current color is white, so if you encounter something like black or blue or green, so you do not need to change that color, so it is a boundary, right? If it is not same as current color, then again you have to go back, so you can return, right? And there is one more case, you encounter a cell which is of new color. That means you wanted to fill 5, and the cell that you're visiting is also 5. That means basically it is the case that a cell is already visited, or by default it was painted of the same color, right? Then also you have to go back. So if image of x comma y is same as new color, then also you have to return, right? So what I'm trying to say, that you were here 5, you wanted to paint 5, you painted 5, and you made a call to the top, and it was already 5, right? So maybe you came this way, so it is already visited, it is already painted, so you don't have to go there, you just have to come back, right? If this is not the case, then in DFS what do? We iterate on the 4 neighbors, and we make the function calls, right? In this case we have a image, we don't have a adjacency list, but what we can do, we can easily compute the 4 neighbors, right? So if this cell is x comma y, so this neighbor will be x plus 1. So I'll draw it here. So if this cell is x comma y, this neighbor will be x plus 1 y. This neighbor will be x comma y plus 1, right? And this will be x minus 1 comma y, and this neighbor will be x comma y minus 1. What do we need to do? We need to make DFS call on the 4 neighbors. Now you might say, okay, are we checking the neighbor is visited or not? We are not checking here, but we have made a base case, right? So what we were doing earlier in previous DFS function that we had written, before making the call, we were checking that should I go to this cell or not. Now I'm going to make blind calls, but if the cell is visited, it is going to return immediately from there, right? So both the ways are correct. So either you make a call and then return, or you do not make a call, right? So here I'm going to make a call and I'm going to return from this base case, right? So now making the call is pretty simple. So I need to call flood fill method. So I'm going to give image x plus 1 y, go right, current color and new color. So I'm going to make four such calls. 1, 2, 3, 4. Right? Let us update the values of x and y. So second call is I'm going to make down. So you can make in any order, that's not going to change the final output. Then I can go x minus 1 followed by y, and then I'm going to make x comma y minus 1. So this actually finishes my algorithm. So this becomes my recursive case where I'm recursively visiting all the four neighbors. So, when you make this call, it's going to take you right, and eventually you come back, then you will explore this direction, right? Again, once this call is over, then you explore this direction and so on, right? So dry run, I have already shown it to you. Now we have written the code. Let us test our code on the given input. I think one important step we have missed is the actual painting step, right? So that is going to mark the cells in the new color. So let's write the painting step. Before you visit the neighboring cells, you have to paint the current pixel as well. So you will say, okay, image of xy will be now painted in the new color, right? So that is the main step of the algorithm. So yeah, this looks fine. Now we can actually run our code. So I've made the function call, and then I've written two for loops to print the image matrix. So let's go and run this code. So what is happening? I'm dropping a color 5 at cell 4 comma 4. Let's see what output do we really get. We are getting some output here. Let's try to see this output. So this is 0 1 2 3 4 in this row. 0 1 2 3 4. Basically at this cell I'm dropping a color 5. So this will actually spread color right, nothing is there. So this will get changed. So this will be 5, this will be 5, this will be 5, this should be 5, this should be 5, this should be 5. Then again we come back, we go here 5, this will be 5, this will be 5, this will be 5, 5, 5, 5, right? So yeah, I think this should be the correct output. We have four fives, two fives, four fives, yeah, and we have one five and two fives. That seems correct. So basically, this kind of a shape will get repainted in this color, right? So I hope you have really understood this algorithm. The code is pretty simple, and what we have done, we have simply done DFS, and we have put some conditions to stop this DFS from spreading, right? So one condition is we do not go outside the grid. Another condition is that you were filling white region, but you encountered a different color, right? So maybe you encountered a boundary. So you come back, you do not go into this region. Another is that if it is already visited, that means if something is already 5, right? Now this can happen in two scenarios. One, the image initially had 5, and second scenario, you painted that region as 5. That means it is kind of a visited region, right? So we do not do work here. Otherwise, we paint it and we recursively paint the neighboring cells, right? So I hope you really understood the DFS approach for flood fill. Let us try to understand how flood fill can be done using our BFS based algorithm. So first I will show you a visualization, and then I will do the implementation, right? So let us maybe draw a shape, okay, just a random shape, right? Let's say this is a shape, and I want to fill this with, let's say, orange color, right? So I'll just select some color, right? And the algorithm is BFS, and I want to fill. So I'll drop a color maybe here, and you will see how it's going to get filled, right? This is how it is getting filled, right? What did we observe? So we observed that if you drop a color at this particular cell, it kind of spreads to the neighboring cells. Okay, and this is what we learned in the BFS. At first, these cells would be covered. Then further, these cells are put into the queue and they will try to traverse their neighbors. So if you pop out this one, it will try to cover this. If you pop out this one, it will try to cover this is already covered. This. Talk about this cell, it will cover this, and so on, right? So in a way, it's going to be in like this order. The color is going to spread evenly in the four directions, right? So if I show you once again, if I draw maybe drop a color here, right, maybe outside, you can see it, the way it is spreading out, it is radially kind of this is how it is trying to spread out, right? Because each cell is trying to paint the four neighbors, right? Now in order to implement this, we will need a queue like we did in BFS, right? And the remaining logic, it's going to be remain similar. So I have created a one empty function flood fill BFS. We are getting the same parameters: image, xy, current color, and new color. So let us finish the code and I will explain you the steps side by side. So first of all, what do I need? I need to implement a queue, right? So I will create a queue. So linked list class provides me with the implementation of queue. But in queue, what kind of data I'm going to push? So now each cell is represented by two coordinates, right? Basically, I need to create a pair of the coordinates to push it into the queue, right? So I have implemented a pair class where I have first and the second attributes, and I have a simple pair constructor that sets the first and the second attributes. So let us go here, right? So I would say linked list of pair. The name of the object is called queue. This is equal to new linked list. And in this queue, I'm going to initialize it with the source node. So I can say queue dot add last. It needs a pair. So new pair of x comma y, right? Now this is in the queue, right? So maybe this cell has some xy. So I push it into the queue, right? So this xy is there into the queue. So next time I'm going to pop out this node and I'm going to traverse, I'm going to paint the neighbors which are having the same color, right? So I'm not going to paint this one, but I'm going to paint these twos because they are having the same neighbors. So I'm going to push them into the queue, right? So I can say while the queue is not empty. So while the queue, okay, it is queue, right? While the queue is not empty, what do I need to do? I need to pop out one pair. So I can say, okay, pair P, this is equal to queue dot remove first, right? So this will be pair P, right? Okay, how do I access the current cell? So I can say, okay, the current x is P dot x, P dot first, pair has these two attributes. Current y, the current y that I've popped out from the queue. So it's going to be P dot second. Now what you need to do? You need to paint this cell. Okay, you need to paint this cell. So painting means we are kind of marking this as visited. So I can say, okay, image of cx and cy. This will be marked with the new color that I'm getting. So I basically change the color, right? Now of course I have to find out the neighbors. Basically I need to find out the four neighbors and push them into the queue, right? Push them into the queue. Now in case of recursive, we can just make a call on the neighbor and we can return, but since it is a iterative algorithm, we cannot push every neighbor into the queue. We have to take care of conditions, right? Now suppose this is the cell and this is outside the grid, so I do not need to push this neighbor. Now suppose this is the cell, this cell is having a different color, so this is black. I cannot push this neighbor into the queue. Maybe this is open, this was one, this was one, and this was one, right? So in such a scenario, I just need to push this one and this one. into the queue because it is having a different color, right? So I cannot push this one, right? So I update the color of this maybe to 5 and I will push these two into the queue. Next time we will pop them out and they will try to cover their neighbors, right? Okay, so something like this it's going to happen. So now how do I find out the 4 neighbors? Of course, one way is we can just hard code the parameters here, right? Or other ways I can use a loop as well, right? So personally, I like writing the loop. So I've not shown you the loop in this one, but we could have done a loop here as well. So how do I write a loop? So basically, you have to think of 4 directions, right? So if this cell is xy, so what is happening here? So the x is getting incremented by +1. Here the x is same. Here x is decremented by -1 and here x is same, right? So if I look at the delta change in x, right? So I'm going to create a array here, delta x, right? So delta x is going to be like 1 0 -1 0, right? So I'm writing in this direction, right? What about delta y? So in this direction y is not changing, so delta y is 0. If I go down, the y is incremented by 1, right? And if I go here, the delta y is still the same, and if I go to the top, the y is getting decremented by -1, right? So the change in y is 0 1 0 and -1. So I'm going to create a delta y array. So it's going to be 0 1 0 and -1. Now you might ask, where do we need this array? So this is going to be helpful. Now suppose if you want to go into this direction, you can say okay, x plus delta x of this direction. So let's give this index 0 1 2 and 3. So these are 4 directions, right? So delta x of 1, basically x will be incremented by 0, and if I go down, y will be incremented by delta x of 1, right? So first direction, right? So y will be incremented by 1, right? So instead of just hard coding the 4 things, we have summarized them here, right? Now how do I find the 4 neighbors? Pretty easy. I know there are 4 directions. So I equal to 0, I less than 4, I plus plus, right? So what is the neighbor of x? So neighboring x is nothing but current x plus delta x, how much I have to change, right? Similarly, neighboring y is nothing but current y plus dy of I, delta y of I. So this is my neighboring x, this is my neighboring y. So I got the 4 neighbors. Now there are conditions on these neighbors we need to impose. This neighbor should not be outside the grid, or I want to push this neighbor if it is inside the grid and it is having the same color as the current color, right? So what is the condition to push? If this is a cell, right, x comma y, this is of a different color, this is outside the grid, this is inside grid. So this is neighbor, this is neighbor, this is neighbor, this is neighbor. So I cannot push this, I cannot push this, but I can push this, I can push this. So the condition is it should be inside the grid and it should have the same color as the current color, right? So I can say okay, if x is greater than equal to 0 and x is less than n and y is greater than equal to 0 and y is less than m. Okay, I need to define n and m as well. So and they should have the same color, right? So if it is white, I want to have it as white. Only then I can paint it. So I can say okay, image of neighboring x comma neighboring y. Actually this will be nx and ny actually. Neighboring x. We are talking about neighboring y and neighboring x. Yeah. Neighboring y. And image of neighboring x and neighboring y, the color is same as the current color, only then I need to push it. So I can say q dot add last new pair of neighboring x and neighboring y. So I need to define n and m. So n is image dot length and my m is going to be image of 0 dot length. So I think this completes our BFS. We have traversed on the neighbors, and the valid neighbors they have pushed into the queue, and this we are doing while the queue is not empty, and here we are painting the cell, right? So this will reverse all the neighbors which are of same color, right? And let's try to run this code now. So earlier I had done the DFS call, now I'm going to do the BFS call with same parameters, and let's see, do we get the same output or not? Ideally we should get the same output. So if you look carefully at this shape, so I dropped the color 5 at this cell maybe. So this whole component should become 5, and even this one also, right? So this should become 5. Let's see, are we getting the same shape? Yes, we are getting the same shape, right? So you can see how this floodfill is working, right? So while we are getting the correct output in this case, but there is one problem with this algorithm that I'm going to show you. Let us try to understand what is happening when we are doing this BFS. We started with this node, this particular cell. We pushed this into the queue, the corresponding um, coordinate. Okay, let's say the coordinate is A. So I pushed this A into the queue, right? Next time I removed this, I painted it 5. Okay, so marking this means painted it 5, and I pushed the neighbors. So neighbors which are of the current color. So this 2 and this 2, only these are the two neighbors. Let's call it B and let's call this neighbor as C. So I pushed the neighbors B and C into the queue. Next time I removed B, I painted it 5, and I again pushed the neighbors into the queue. Let's say this neighbor uh, D and this neighbor E. So D and E, they are also pushed into the queue. Next time I will remove C, right? I will remove C, and I will again push the neighbors. Now one neighbor is this. I will of course paint it. One neighbor is this, and but this is already into the queue, right? And this is also going into the queue. What is going to happen, that some neighbors like this node, they will be present into the queue multiple times, right? So if you do not believe me, I will show you. So I have written a statement that okay, when the queue is while the queue is not empty, I'm going to remove a particular cell. So if we get the same coordinates again, that means a particular cell has been pushed into the queue multiple times in this algorithm. So we need to fix that, right? So removing 4 4 5 4 3 4 4 3 5 5 5 3, okay, 3 3 3 3, right? Look at this 3 3. So this 3 3 is present into the queue two times. What is this coordinate 3 3? Let me show you. This was 4 4, right? No, 0 1 2 3 4. Okay, this was 4 4, right? 0 1 2 3 4, right? So it might have discovered this, basically this cell, right? So it was entered by this neighbor also, this neighbor also. We want to avoid this, right? So in order to fix this, we need to go with the visited array thing, right? So like in BFS, we do maintain, okay, whether a node has been visited earlier or not. Same thing we have to maintain here as well. So what I need to do, I need to maintain a boolean visited array. So this part I can move a bit here, and I can say okay, I'll need a visited array. So boolean visited equals new boolean of the size n cross m. By default everything is false in Java, so we don't need to set false. Then when you're adding the first node, you can mark this as visited. When something goes into the queue, you have to mark it visited. So visited of x comma y, this is equal to true, right? And then when you're pushing again something into the queue, you have to say visited of x comma y, this is equal to true. And then again when you're checking that should I add this cell into the queue, so you should add if it is not visited. So not visited nx and ny. So here also it will be nx and ny, the neighboring x we are talking about. So I think this now is close to the actual BFS logic that we have implemented. This visited thing is important. I've shown you why. And now there are three conditions here, right? I think this, it's better to put it here. And ny is less than m, and not visited nx ny, and image color is equal to current color, right? So three conditions now: visited, color condition, within the bounds, right? Now let us run this code, and now we should not see duplicate cells here. 445434355333655632753176. Are we still getting the same output? Yes, we are still getting the same output, and this is the correct way to implement the algorithm, right? So I hope now you have understood the importance of visited array and the implementation of flood fill using BFS. So that's the end of this tutorial. I hope you learned a lot of concepts. So if you like the lecture, please make sure you like the video, share it with your friends, and subscribe to our channel for more such amazing tutorials. Thank you, and I will see you next time. Hello everyone. Today's tutorial is about topological sorting on graphs, which is a very interesting and useful algorithm. So first of all, we'll discuss what is a directed acyclic graph and what is the concept and need for topological sorting. Later on, we will dive into the applications of topological sorting, and we will also discuss two algorithmic approaches. One is a DFS based approach and another is a BFS based approach known as Khan's algorithm for topological sorting. Not just the theory part, we will also discuss code and we will implement these two algorithms in today's video. But before we get started, make sure to check out free masterclasses on Scalar's event page to learn from some of the best industry experts. Also, subscribe to our channel if you haven't done already. Let's dive right in. Let us start with the definition of topological sorting. So it is defined for directed acyclic graph, also known as DAG. And what is this? It is a linear ordering of vertices such that for every directed edge uv, vertex u comes before v in the ordering. Now what does it really mean, right? So this looks a bit complex. So let me say I have to first understand what is a directed acyclic graph. Basically consider a graph like this. Let's say I have a, it has a directed edge to b, and it has a directed edge to c, and let's say b has a directed edge to c, and it has a edge to d, right? Now suppose this is this graph directed? Yes, this graph is directed. Acyclic, that means the graph should not contain a cycle. So if I draw another graph in which a is connecting to b, b is connected with c, and c is pointing to a, right? Is it a acyclic graph? The answer is no, right? The answer is no. Now think of this graph as a dependency graph. For example, b is dependent upon a, c is dependent upon b, and a is dependent upon c. So if you have to start from one task, right? Let's say this is a dependency graph of tasks. Can you start with any task? The answer is no, because there would be a deadlock, right? In this case, there is a complete deadlock because b is dependent upon a, c is dependent upon b, a is dependent upon c. So there is a deadlock. So we cannot do really anything here, right? But look at this graph. Now suppose each node represents a task that you can do, right? So will there be any deadlock? The answer is no. In this case, there won't be any deadlock. So, and also if you look carefully, there is no cycle here, right? So this is a acyclic graph, and of course it is a graph, right? So hence the term DAG. So the first graph I have drawn here is an example of directed acyclic graph. This is an example of a directed graph, but it is cyclic in nature. Here there will be no deadlock, right? Now let us try to understand what does it mean linear ordering of vertices such that for every directed edge u to v, vertex u comes before v in the ordering. So now b is dependent upon a, right? That means if you need to execute task b, a must be done before, right? If c is dependent upon b and a, that means in order to execute task c, you must do b and a before, and d is dependent upon c, right? So basically d has a dependency on c, c has a dependency upon a and b, right? But the thing is, between a and b, what task you should do before, right? So you should do a, right? So you should do a first. If a is done, then this dependency is removed, this dependency is removed, right? Then you can do b. So if b is done, dependency of c is removed, you can do c. And if C is done, dependency of D is removed, you can do D, right? So this order of vertices is called topological ordering of vertices, right? So that for every directed edge U to V, vertex U comes before V in the ordering, right? So there is an edge from A to B, so A is coming before B. There is an edge from A to C, A is coming before C. There is an edge from B to C, B is coming before C, and there is an edge from C to D, C is coming before D, right? So you can see all the edges, they are in this direction. So from any vertex U to any vertex V. So I hope you understood the definition of topological sorting. And now we will discuss one more example where this kind of algorithm might be useful. So you have got a fairly basic idea about topological sorting. So ideally, the main use case of this kind of algorithm is in resolving a dependency graph, right? So main use case will be resolving a dependency graph. Of course, there are many more applications which we will discuss at the end of this tutorial. But what this algorithm is doing, it is resolving a dependency graph. Now, where this dependency graph? So one example I can give you is that when you are installing some kind of let's say libraries on your server or some modules on your server, right? So it is possible that there is a module A or there is a module B which is dependent upon A. There is a module C which is dependent upon B. There is a module D which has a dependency upon B and A. There is a module E which is dependent upon E and C, right? Now, if you have to install all these modules on your server, right, you cannot say I will install E first. No, I cannot install B first, right? So there has to be a specific ordering. In this case, that ordering might look like you go with A, then you go with, let's say, B, then you can go with, let's say, C. Okay, but if there is an edge from here to here, then you have to go with D first, then you can go with C, and then you can go with E, right? So the installation has to proceed in the following steps, right? In the following order, right? So this is where software needs to construct a dependency graph of the modules that needs to be installed because there are certain dependencies, right? So this is one example from the computer science world. Just to keep things simple, let us try to understand from a real world example. So we are taking an example of baking cake, right? We are saying, okay, in order to bake the cake, there are certain steps needs to be followed. For example, you have certain ingredients: flour, baking powder, baking soda, yogurt, oil. Before you put all of them into baking, you have to mix all of them, right? So basically there is a dependency. You have to mix the ingredients and then you can bake, right? Then, but if you, before you actually put this into the pan must be greased and flowed properly, right? So basically, before putting the ingredients into the pan, what you have to do, you have to grease and oil the pan, right? Again, there is a dependency. Before you put the ingredients, you have to grease the pan, right? Once you have poured the batter, you know you need to bake it well. But again, before you bake, you must preheat the oven. So again, there is some dependency, right? You have to preheat the oven before you do something, right? To ice the cake, it must be cool. But to cool, you must bake it first. So basically, before you cool the cake must be baked. Again, there is a dependency. The cake has to be cooled before you can actually ice it. So icing has a dependency on cooling. Cooling has a dependency on baking. Baking has a dependency on mixing. And of course, there is some dependency between pan and putting the ingredients, right? Now, this looks like there are various tasks and there are various dependency for each task, right? But of course, there would be some tasks which do not have any dependencies. Those form the starting point of our topological sorting, right? So if you visualize all these steps in the form of a graph, it will look something like this, right? So preheat oven, now this does not have any dependency. Greasing the pan, this does not has any dependency, right? So you can say, okay, in the beginning I can do this, I can do this, this can be one, this can be two, or this can become the first step, this can become the second step. And of course, once this is done, you cannot of course jump into baking, right? So you have to do this stuff as well. You have to mix ingredients, add it to the pan. This can become 3, this can become maybe 4, this can become 5. And of course, if you follow all these steps in a particular order, you will be able to bake the cake, right? So I hope you understand the concept of topological sorting is used in resolving dependency graphs. Now we will look at two algorithms to do this. So let's begin with the algorithms now. Let us discuss the implementation of topological sort. So right now I want to complete this function topological sort, which does not get any input. So we have to pick what is the starting point, from what node should I really start, right? So just like DFS, we will build this method, right? So first of all, we will build a Boolean visited array, which is going to be a Boolean array for all the V vertices. Apart from it, I need a list of integers that will actually store the output. So this is going to be, let's say we use a array list, and initially it is an empty list, and you can mark everything as not visited. So again, that is completely optional. So if you want to explicitly set everything to false, you can use arrays.fill method, and you can set everything to false. Nothing is visited in the beginning, right? So in the graph, when we were doing DFS, we knew the source. What is the starting point? Here we do not really know the source. Now suppose if my graph is like this. Let me draw a graph. Let's say I have 0, 1. It is connected with, let's say, 2. 0 is also connected with 2. It is connected with 3. Then it is connected with 4. Like this, and like this. Now this is an example of a directed acyclic graph. Now, should I start with 0? Should I start with 1? Should I start with 3? I really do not know, right? So what I will do, I will put a loop and I will start from every node that is not visited, right? Or let us just assume that we start from node 0. Will it traverse the entire graph? The answer is no. So if you start from 0, you visit this node, then you go to 2, you visit this node, maybe then you go to 5, you visit this node, and then you backtrack. So you put 5 into your list. You come back to 2. Can you go anywhere else? Yes, you can go to 4. So you visit 4. Now you again backtrack because you cannot go anywhere else. So you put 4 into the list. Now what happens? You come back at 2. You cannot really go anywhere. You cannot go anywhere. So you again backtrack. So you put 2 into the list. You come back at 0. You cannot go anywhere. You put 0 into the list, right? So if I do it this way, because there can be many starting points. So you can start with 0, you can start with 1, you can start with 3, and so on, right? So there can be many starting points, but if you start from, let's say, 0th node, you are not able to traverse the entire graph, right? So again, there are nodes 1 and 3 which are not yet visited. So what I will do, I'll say, okay, I will put a loop for I equal to 0 for all the vertices. If a node I is not visited, I will again make a call to visit the graph from that node, right? So now I discover, okay, from 0 I made a call, this is visited, 0, 1, 2, 3, 4, 5, right? So I can say, okay, is 1 visited? The answer is no. So I can make a DFS call from 1 as well, right? So I can say, okay, go and visit. From 1 you start, you cannot go to 2, but you can go to 3, right? So you visit 1, you visit 3. Now from 3 you cannot go anywhere, you backtrack. So you put 3 into the list, and then again you come back at 1, you cannot go anywhere, you put 1 into the list, right? And then you reverse this. So you get 1, 3, 0, 2, 4, 5. Is it a correct order? The answer is yes. From 1 to 3 there is an edge. From 0 to 2 there is an edge. From 1 to 2 there is an edge. From 2 to 4 there is an edge. And from 4 to 5 there is an edge. From 2 to 5 there is an edge. From 3 to 4 there is an edge, right? So you can see all the edges are in this direction, and hence this ordering is actually correct for this graph, right? Of course, many orderings are possible. You can have an ordering in which 0 and 1 are coming first because they do not have any dependency, right? But this is also correct. So if I do it using DFS, this might be the order I will be getting, right? So what I will do, instead of saying that always start from node 0, I will say, okay, always start from a node that is not yet visited. So I equal to 0, I less than v, I plus plus. Now, of course, the same DFS function will not exactly work. We have to add the backtracking step in our DFS code as well. So I will write a separate function, void topological sort helper, which is essentially nothing but a DFS function. So this is going to accept the node at which I am currently at. I'm going to give a Boolean visited array. Then I'm going to get an output array as well. So I can say int output. So this is a array list. So let's just keep it as list of integers, right? So I'm getting the output array as well, right? So maybe I'll scroll a little bit, right? When you're reaching a node, what is the first step? So you print it, but here we don't need to print it. We need to push it into the list while going back, right? So we'll mark the node as visited. So we can say, okay, visited of node, this is equal to true. Then I will iterate on the neighbors. So what are the neighbors? Of course, we have to initiate the call as well. Topological sort helper. So this call will be done if a node has not been visited, right? So if not visited I, right? See, when you call from 0, you have visited 2, 4, 5, right? So you will not initiate a call from 2, 4, 5, but you will initiate a call from 1, right? So I'll give ith node, I'll give the visited array, I will get the output array, right? So I think this function looks complete almost. So we have to return the output as well, and we have to reverse the list collections dot reverse output, right? So this is the wrapper function for topological sort, and here is the DFS call that we are making. This is output, right? So I have to mark the node as visited, then I have to traverse the neighbors which are not visited, right? So traverse the not visited neighbors recursively, right? So this thing is pretty simple. We can use the same logic that we did in DFS. We'll create an iterator, we'll iterate over the adjacency list, and we'll make a recursive function call. So I'll just copy paste this code here. So we have an iterator. So if the node is 0, the neighbor is just 2. If the node is 2, the neighbors are 4 and 5. So we'll iterate to get the neighbor, and if it is not visited, we will make the call to topological sort helper neighbor visited, and the third is output. We need to give it, right? So once it is done, what do I do? Now I can say, okay, yes, I have visited all the neighbors from the given node. Now I'm going to backtrack. I'm going to go back. So in this step, what I will do in my output, I'm going to add the current node, right? That's it. That completes my backtracking step, right? So let us first run our code and see, are we getting the expected output? So I'm going to go into the main. So I've already created this graph, right? So this is the same graph, you can verify, and I've called the g.topological sort method. So let's go and see what output do we really get. So adjacency list will depend upon in what order we have. So we are actually getting 130245, which is exactly same as this 130245. That means the algorithm is working absolutely fine. If you want, I can give you a quick dry run of this algorithm, right? What I did initially, nothing was visited. Let me do it with blue color. So I start with 0. 0 is not visited. I visit this node, and I see this is not visited. I make a DFS call, that is topological sort helper, from this node. And what this function does, it marks this node as visited. So this is visited now, and we iterate over the neighbors. So the neighbor is just 2. 2 is not visited, so we make a call to 2. Okay, again 2 says, okay, what are my neighbors? The neighbor is 5 and 4. Maybe we make a call to 5. We go here, and 5 says I don't have any neighbors, so this loop is complete for 5, and I'll say output.add. So this 5 is added in my output, right? And now I go back. So I come back from 5 back to this node. So at 2, I see, okay, I can go to 4. So I make a call to 4. 4 says, okay, I cannot go to 5. So 4's neighbor is just 5. 5 is already visited. I cannot go there. So I just try to go back. So I add 4 into my list. I come back at 2. 2 says I cannot go any further. So I just backtrack. So I add 2 into the list and go back to 0. 0 says I cannot go any further. I add myself to the list, and that's it. So this recursive call is complete. Now we come down here. We check, okay, 0 is visited, fine. Is 1 visited? The answer is no. 1 is not visited. So I again initiate a DFS call from 1. Okay, from 1 I cannot go to 2, it's already visited. Can I go to 3? Yes, I can go to 3. So I go to 3, I mark it visited. From 3 I cannot go any further. So I just come back. So I push 3 into the list using the above code, right? And from 1 I cannot go any further, so I push 1 into the list. Finally, this list is ready, and here I reverse this list to get this output, which is reflected here, right? So I hope you have understood the code. It's pretty easy, fairly simple. The only change that we have made is we are adding the node here, and since all the nodes might not be visited, so we initiate a DFS call from every part of the graph which is not visited, right? So finally we return the output, and that is printed. So that's about the implementation of topological sort using DFS. Let us discuss one more algorithm for topological sort. This is popularly known as Kahan's algorithm, and it is a BFS based algorithm. So the first step of this algorithm is you always have to start with vertices which do not have any incoming edges. That means zero dependency. Okay, so no incoming edges. So I'm going to define a term that is called as in degree. So in degree is basically number of edges that are entering every node. What we will do, we'll construct a in degree array by reading the adjacency list. So if you have the adjacency list, that might look like this. So 0 is connected with 2 and 5, 1 is connected with 2 and 3, 2 is connected with 4 and 5, 3 is connected with 4, 4 is connected with 5. I guess I have covered all the edges, 2, 4, 6, 8. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So what we will do, initially in degree of all the nodes is 0, and then we will say, okay, from 0 to 2 there is an edge, so in degree of 2 it's going to be 1. 0 to 5 there is an edge, so in degree of 5 is going to be 1. 1 to 2 there is an edge, so in degree of 2 will be incremented by 1. 1 to 3 there is an edge, so this will be 1. 2 to 4 there is an edge, so this will be 1. 2 to 5 there is an edge, so in degree of 5 will be incremented by 1. 3 to 4 there is an edge, so in degree of 4 will be incremented by 1. 4 to 5 there is an edge, so in degree of 5 will be incremented by 1. This in degree will be now 3. So if you look carefully, what you will get, you now know how many edges are entering each node. So if you talk about 5, 3 edges are entering 5, right? So from the adjacency list you can easily create this array, right? Now this array contains one very important piece of information. What is that information? That what are the nodes which have actually 0 in degree. So we know that 0 and 1 they have 0 in degree, right? So what I will do, from this in degree array, we will use another data structure that is used in BFS. So this data structure is queue, right? So we will queue up all the nodes which do not have any incoming edges. So we can traverse this array and we find out 0 and 1 are the nodes which do not have any in degree. So that means these are the tasks I can perform without waiting for anyone, right? So I can directly execute 0. Now suppose I pop out one node, I execute this task 0. So 0 is gone, 0 is printed, and these connections, these edges are now lost. Why? Because these dependencies are gone, right? These dependencies are gone. So I'll just make them dotted, right? Or I can just erase them, that's fine, right? If I do this, that means in degree of 2 and 5 they will go down. So in degree of 2 will be now 1, and in degree of 5 will be now 2, because one edge has been gone, right? So you pop out this node, you print it, and you decrement the in degree of edges originating from this node. The next node you can pop is 1. Okay, if you look at 1, it can be removed, yes. So you will print 1 and you can remove this edge. That means in degree of 2 will be now 0, and it should be added into the queue, right? Because now this node is ready, and 1 also has this edge, so this will be also removed. So in degree of 3 is also going to be reduced by 1, so this in degree is also 0. That means 3 is also ready to be processed. There is no dependency, so you can push 3 into the queue as well, right? So next you can pop out 2. So 2 will be removed, you will print 2, and you can delete these edges. That means in degree of 5 will be reduced by 1, so this in degree will be 1. So right now I'm not going to push 5 because it still has a dependency. What about 4? 4 in degree is 2, so it can be removed, it can be reduced by 1, so this in degree is going to be 1. Okay, and of course these edges are gone, right? These edges are gone. That means now what is the thing we will pop out? We can pop out 3. We will say, okay, fine. We will print 3 and then we will remove it, right? That means this edge will be gone. So in degree of 4 will become 0. So if in degree of any node becomes 0, you have to push it into the queue, right? Add it to the queue. Next, you will pop out 4 and you will print 4 and this edge will be gone, right? That means 4 is printed. In degree of 5 is now 0, right? Because 4 to 5 there was an edge, right? So in degree of all the neighbors of 4 will go down by 1. So this will become 0 and that means now 5 is ready to be processed. So you push 5 into the queue, then you finally pop out 5, you print 5 and you can see queue is now empty. That means we are done with the algorithm and we will stop, right? So pretty easy, right? So I hope you understood the algorithm. Next we will look at the implementation in Java. So let us implement this algorithm that we have just discussed. So first of all, I'm going to create an array that is going to store the in degree for every vertex. So it will be an array of integers. So I can call it as in degree. And I know there are v nodes, so I will create an array of size v. So new int of size v. So initially I can say everything will be 0. So I'm going to fill this array with 0 values. And now I'm going to build this array. So for that I need to travel through the adjacency lists. So I have v nodes and for every node there is a adjacency list. We need to create a list iterator like we have done earlier and we need to iterate over the list. So I'll just copy paste some code here. We don't need the visited thing here because it's not a cyclic graph and we are doing BFS. So I don't think visited array will be needed here. Okay, and we did not use it in the algorithm as well. So I can say, okay, I'm going to create an iterator for the ith node. Then I'm iterating over the ith node. Now suppose there is edge from, let's say, ith node to nodes x, y, and z. In that case, what will happen? Your in degree of x will increase, y will increase, and z will increase. So I'm just generalizing this with the term neighbor. So in degree of neighbor will be incremented by 1. So I'm going to say, okay, fine. Let me say in degree of neighbor plus plus, right? So after this for loop, I will have in degree of every node. So create a, or I can say basically update the in degree array. This is what I'm doing. I'm going to set the initial values here, right? So update the in degree array. So these are the initial values, right? So right now we have not started the BFS. We have just built the in degree array, right? And I'll also create one more data structure that is going to be the queue for the BFS. So I can say, okay, queue of integer queue, this is equal to new linked list, right? So linked list is the class that provides implementation for the queue interface. And then we can say we'll need one more data structure that is the output, in which I'm going to store the output. So that can be a array list or it can be a array. So I prefer array list here. So I will say, okay, list of integers, let's call it as output, and this is equal to new array list. So this we will use in our algorithm, right? Now the next step of the algorithm would be that you want to do BFS, so you need to initialize your queue with all the nodes that have 0 in degree. So for that you have to travel through the in degree array. So you have to traverse in degree array and find nodes with 0 in degree. That means they can be the starting point, they don't have any dependency. So I can say, okay, for int I equal to 0, I less than v, I plus plus. If in degree of ith node, if it is 0, then this can be added into the queue. Now you have initialized your queue and now you can do your BFS, right? So you can say while my queue is not empty, I will remove something. So I can say, okay, node is queue dot poll. Now you will, suppose you removed a node. Suppose you removed a node 0 and it was connected with some other nodes, right? 0 was connected with this node, right? Let's say 1 and 2. So we'll say, okay, whatever the neighbors of 0, since these edges are now going to be removed in degree of 2, which was 2. There were 2 incoming edges. So it will be reduced by 1, right? So I need to again find the neighbors of this node. So we'll again create an iterator for this to iterate on the neighbors of this node. So I can say, okay, so while iterator dot has next, what to do? I need to get the neighbor. So my neighbor is it dot next, and I'm going to say in degree of neighbor will be reduced by 1. Now suppose if in degree of that neighbor after updating becomes 0, okay, so that means that neighbor is available to be processed. So I will add it to the queue. Queue dot add neighbor. So I've added the neighbor into the queue. That's it. Now when you remove this node, that means it was not having any dependency, right? So we will need to add this into the output. So output dot add. That's it. And from this function I need to return output. So you can see we have implemented all the steps that we have discussed. We are pushing nodes into the queue with 0 in degree. Then we are iterating over the neighbors. We pop out one node, we iterate over the neighbors. We reduce their in degree by 1. And if some point in degree becomes 0, we add that neighbor for future processing, right? So I think this should work. So now let's go and run our code. Let's go to topological sort main. I'm calling the method topological sort BFS. Let's run this. So this is the method, right? So we are getting 0, 1, 2, 3, 4, 5 for this graph that we have discussed. 0, 1, 2 is here, 5 is here. This is like this, this is like this, and this is like this, right? So 5 is printed at the last, so 0 and 1 we can start, absolutely correct. And we have 2, 3, 4, 5, right? I think this looks correct, the output is correct. And regarding the code, we have already discussed the algorithm in detail. I don't think there will be any doubts. If you have any doubt, please comment it down, right? That's all for this algorithm, and we are done with the topological sort. So you have understood and implemented topological sort. This algorithm has many other applications as well, such as cycle detection in graph. In operating systems, it can be used in deadlock detection, because deadlock is also kind of a cycle. If you know how to find a cycle, you can also detect a deadlock. Then there is dependency resolution, which we have already covered. It is also used in sentence ordering, critical path analysis, course scheduling problem, manufacturing workflows, data serialization, and context-free grammars. So if you're interested, you can dive deep into these applications and learn more about how this algorithm is actually used in building these applications. So before you leave, make sure you like the video, subscribe to our channel, and I hope you learned a lot from this tutorial. Hello everyone. In today's tutorial, we are going to talk about traveling salesman problem, which is a very popular graph algorithm and can be used in variety of applications such as route design of Amazon delivery vans, school vans, and many other applications. But before we get started, make sure to check out free masterclasses on Scalar's event page to learn from some of the best industry experts. Also, subscribe to our channel if you haven't done already. Let's begin with the tutorial. Let us start by understanding the problem statement first. So the problem statement says, given a set of cities, it could be set of anything. It could be set of nodes, set of landmarks, set of cities, and we are also given the distance between every pair of cities. That means it is kind of a complete graph where every node is connected with every other node, right? So we know the distance between every pair of cities. So the problem is to find out the shortest possible route that visits every city exactly once and returns to the starting point. So basically we need to do a cyclic tour in which we are covering every node in the graph and we are coming back to the source. For example, if I take an example of an Amazon delivery van, so the source may be warehouse, right? And from this warehouse, it has to drop packets to the customers. So maybe customer 1 is here, customer 2 is here, customer 3 is here, customer 4 is here, customer 5 is here, customer 6 is here. Now, in what order I should visit these customers so that this tour cost is actually minimized, right? So now there can be various ways to cover these customers. Okay, maybe this is cost X, this is cost Y. It is possible that I could have taken this edge. This edge was Z, but I have not taken this edge, right? So we have to design an optimal delivery route covering all the nodes and coming back to the source node. So in other words, this problem is also about finding a minimum weight Hamiltonian cycle in a complete graph. What is a Hamiltonian cycle? I would also touch upon this term briefly. Let's try to understand what is the difference between Hamiltonian path, Hamiltonian cycle, and how this traveling salesman problem is related with Hamiltonian cycle. So let us touch upon these terms. So first of all, I'll show you the input. The input is a complete graph. So what is a complete graph? In which we know the distance from every vertex to every other vertex, right? So we know if there are 4 vertices, right? Then there will be how many edges? Between every pair of vertices we will have an edge. So there will be 4C2 edges, that is 4 into 3 by 2. So we will have 6 edges, right? So in case of a graph with n nodes, we will have NC2 edges. That is what a complete graph looks like. Now, if we'll touch upon briefly about how do we represent this graph. So in such a scenario, it's a very dense graph. It is a complete graph. So the most suitable data structure in this case would be adjacency matrix, because we know that we have number of edges that is proportional to n square, right? We have almost n square edges. So this is how this matrix is going to look like for this graph. But before we dive into the algorithm, let us talk about what is Hamiltonian path and Hamiltonian cycle, right? So a Hamiltonian path in an undirected graph is a path that visits every vertex exactly once. So if I talk about the previous diagram, maybe I start from A, I go to B, I come to C, and maybe I go to D. Will this be a Hamiltonian path? Yes, because this is a path that covers each vertex exactly once, right? Whereas a Hamiltonian cycle or a Hamiltonian circuit is a Hamiltonian path such that there is an edge from the last vertex to the first vertex of the Hamiltonian path. So basically it's a cycle. That means you have to loop back to the starting node, right? So generally the problem of Hamiltonian cycle is about check whether a given graph, it's not about complete graph, it's about any graph contains a Hamiltonian cycle or not, right? So given a graph, we have to tell whether such a graph contains a Hamiltonian cycle or not. So basically, is there a path in which we can cover all the vertices and we can still come back to the main vertex? Yes, this is like one path. So it's a complete graph. It can actually have many paths. Maybe I go from A to D, A to C, then I go to B, then from B I go to D, and from D I go to A. This is also an example of a Hamiltonian path. So what I'm doing? I'm doing A, C, B, D, A, right? So this path will be actually a Hamiltonian cycle because we are coming back to the original vertex, the source vertex. Okay, so this will be called as a Hamiltonian cycle, right? If I remove this last edge, it will be an example of a Hamiltonian path, right? So I hope you're understanding the difference between Hamiltonian cycle and Hamiltonian path, and they are defined for any graph, right? So if a graph contains a Hamiltonian cycle, it is called Hamiltonian graph. Otherwise, it is called non-Hamiltonian. So finding a Hamiltonian cycle in a graph is a well-known problem and with many real-world applications, such as in network routing and scheduling. So this is a separate problem in itself. Detect whether a graph contains a Hamiltonian cycle or not. So right now in this video, we are not talking about this problem. So again, this is another example of a graph which is not actually a complete graph. This is not a complete graph, right? But still what I want to do, I want to tell whether this graph contains a Hamiltonian cycle. So maybe yes, I can go to 0, 1, 2, 4, 3 and loop back to 0. So this is an example of a Hamiltonian cycle, right? So this set of vertices I will cover in this order, it becomes a Hamiltonian cycle. Again, this is not a complete graph. So Hamiltonian cycle can be present in a graph which is not a complete graph, right? Now, what is the relation between traveling salesman problem and Hamiltonian cycle? So the Hamiltonian cycle problem, as I discussed, it only checks whether there is a tour that visits every city once and comes back to the source city, right? Now we know that in TSP, a Hamiltonian tour will always exist because the graph is complete. You know, from every vertex to every other vertex, there is an edge. So it is always possible to generate many tours, right? Many such tours exist. The problem is to find out the minimum weight Hamiltonian cycle. So one cycle that has the minimum weight, the minimum cost of traversal, right? So out of all the tours, I want to find out the minimum cost tool. So that is my TSP problem. Okay, so what I already know, that because of complete graph, there will be a Hamiltonian cycle, but what is the minimum cost Hamiltonian cycle? That is something I need to find out. So I hope you have understood the problem statement. Now we will dive into the algorithm and understand it through an example. Now we would like to build an algorithm for maybe this sample graph that gives me the minimum cost of the two, right? Now I can start from any node, right? I can start from A, I can go to B via this edge, I can go to C also, I can go to D, and then I can come back to A, right? So this could be like one tour, and this tour will have some cost. What is that cost? That cost will be 20 plus 30 plus 10 plus 25. This cost comes out to be 85. I do not know whether this is the minimum cost or not, right? But what I'm trying to tell you is, of course, you can have many other tours, right? In different order also, right? But what I'm trying to tell you is that this is like a cyclic tour. You're going from A, B, C, D, and A. If you keep this tour and you can start with any node, you can start with B also. You can go, okay, I will go from B to C, then from C to D, then from D to A, and again from A to B, right? So basically, this is like a cyclic permutation, right? So this tour will also have the same cost because you're exactly covering this set of edges that we have shown here, right? Basically, what is the first observation? That the starting point does not matter because it is a cycle. The starting point or which node I should start with, it really does not matter. But second thing is, if I'm building a brute force algorithm, I actually have to look at all possibilities, right? So that means if I start with A, right, A, B, C, D, right? So this could be like one particular order, right? I can actually have all the n factorial permutations of this, right? Because if no, I know the starting point, the ending point has to be A. So this does not really matter. If I permute it in a different way, maybe I do B, C, D, A. Can I do this? Of course I can do this, right? So from A, B, C, D, I can have a permutation like B, C, D, A, right? Maybe. Or this is from B, I can go to C, D, A, and I can come back to B. This is one permutation, but it has the same cycle. Maybe I can do B, D, A, or I can do B, D, C, A, something like this. So I'm saying B, D, C, A. So whereas B, I can go to D, I can go to C, I can go to A. The last point I know, it will be same as the source point. So this will be B, right? So again, this is like one permutation, right? So basically all the tours, each tour is nothing but it is a permutation of ABCD, right? You can permute these nodes in n factorial ways, right? So that means I will have n factorial possible tours in my case, right? But one thing I'm going to tell you is that the starting point really does not matter, right? So why don't we fix the starting point? We can fix A as our starting point or B as our starting point because that really does not matter. So what I can do is I can make it little bit optimized. I can say, okay, the starting point is A. I can simply permute BCD, right? So that means I will actually have n minus 1 factorial tours. So maybe ABCD is one tour, ABDC is another tour, ACBD is another tour, ADBC. Like I can have like six tours here, right? And this last point I know it's still going to be A. It's going to end at A, right? So what I'm trying to say is, if I have to do a brute force algorithm, the number of tours will be n factorial or n minus 1 factorial. Again, if you want to keep B as a starting point, those tours will be repetitive in nature. Those will be something you have already covered here, right? So starting point we can fix, and rest of the nodes we can permute in any order. Each order will give us a different tour, right? For example, if I talk about A, B, D, C, so you go from A, B, D, C, and again you have to come back to A, right? So this is another tour, right? This will have a different cost. So the cost will be 20. You go here, then it will be 34, then it will be 10, then it will be again going back. That is 42. This cost comes out to be how much? 52 and 20, which is 72 and 34. So it's going to be 6106, right? So definitely this tour has a much higher cost than we originally calculated by doing ABCD. That was 85, right? So I hope you're getting some idea about brute force algorithm. So the idea here is to generate all possibilities starting from a given node, right? So let us dive into little more detail about this algorithm. So now you know that we are going to build a brute force algorithm in which we are going to fix a starting point, let's say A, and we are going to generate the remaining like permutations of the remaining set of nodes. Okay, so you can start with A, you can go to B, or you can go to C, or you can go to D, any node you can pick, right? What I'm trying to say is that you have A followed by remaining set of nodes, and you have to permute them to get the combination. And I know the ending node must be A, right? So whatever node I end in this sequence, that node must return to A. So if the sequence is ending at D, then I need to know the cost from D to A also, right? So this is something I need to do. And we have fixed the starting point, right? Let's see how we are going to do it recursively, or maybe using DP later on, right? So let's say we have A, right? Now, if I start with A, I know A is already visited, right? So I'm going to maintain what set of nodes I have already visited. So if I talk about, let's say, A, B, C, D in this direction, right? 0, 1, 2, 3, 4. So A is already visited. I can just mark it 1, and remaining nodes are not yet visited. So I can maintain a visited array in which I'm going to mark, okay, A has been visited and remaining nodes are not yet visited. Now, if I stand at A, what are the nodes I can go to? I can go to B. B could be the next node, right? Or I can go to C. C could be the next node. Or I can go to D. D could be the next node, right? Let's say I go to B. I pick this node. So I say, okay, from A, I'm going to B. I'm going to visit this node. And this definitely adds a cost of 20 in my answer. So I can say, okay, the cost of the current edge, that is 20, that should be added. Plus, if I'm doing it recursively, I can say, okay, whatever is the cost from B to complete rest of the tour and going back to A. So that cost, that additional cost, so that will be given by a recursive function that I'm going to make, right? Okay, so if I hit B, I can say, okay, A has been visited, B has been visited. So with B, this Boolean array will look like this: 1, 1, 0, 0. Again, this is ABCD, right? So again, I'm maintaining what nodes have been visited. Because I visited A and B, I cannot go to them again, right? Now, what are the nodes I can actually cover? I can go to C or I can go to D, right? From B, I can go to either I can go to C or I can go to D. So let us suppose I go to C first, right? So it will be like 1, 1, 1 and 0. This is again my visited array, right? And what is this cost from B to C? So this cost, if you look at, this cost is actually 30. So this cost will of course get added in my answer. And I can say, okay, plus the remaining cost, the cost from C to cover the remaining nodes and going back to A, right? Now, standing at C, do I know what nodes I can visit? Yes, I need to iterate on this list, and I know clearly this D node is not visited. So it's like doing the DFS, right? So D is not visited, I can make a call. So I can say, okay, fine, let us visit D. So from C, I can go to D, right? And of course, this cost gets added up, that is 10, right? Now, when I reach D, I don't have a choice. I know that I still have to go back to what? I have to go back to the original node, that is A. That is the source node, right? So source node is fixed. So I will say, okay, fine. From D to cover the remaining nodes which are 0 and going back to the source, how much is the cost? This is nothing but you have to return the cost from D to the source node, which is A, right? So that cost is actually 25, right? So this cost you have to return. This will act as a kind of a base case, right? So this cost 25 you will actually return from here. So C will return how much? 10 plus 25, that is 35. B will return how much? 30 plus 35, that is 65. And 20 will return how much? This will be 20 plus 65, that is 85, right? But that is the answer for only one branch, right? In similar way, we have to compute the answers for the remaining branches also and then take the minimum, right? So maybe I have to take the minimum across all branches. Maybe this tour doing A, C, B, D, A. Maybe this might be the best tour, or maybe A, B, C, D, A. This might be the best tour. I really don't know, right? So I have to travel across all the branches and then find out the minimum. So of course we will take the minimum here as well, right? So we have to take minimum here as well. So now the way we are going to do is that, okay, we got to know the answer of this branch A, B, C, D, A. This answer we already know. Now from D, I cannot go anywhere. I have returned the answer. I came back to C. C had only one option, that I can go to D. So again, now what I'm going to do, I'm going to do backtrack, right? So I'm going to say, okay, backtrack from D, go back to C, backtrack from C, go back to B. Now B had two options. B could have said that, okay, let me go to C, which I have already done, right? So when you're doing backtracking, you have to mark these nodes which have been marked as visited as false also, right? So visited of C will be false, visited of D will be false. So when you come back at B, the state of the visited array will still look like this because of backtracking, right? Now at B, you know that, okay, I can go to D as well. So this path I've already explored, so I can go to D as well. So when I come this path, right? So when I take this path, right? So what do I know? The visited array will look like this, 1 0 1 1, right? And now at D, I can say, okay, what nodes I can actually visit. So I can visit C. So I can say, okay, let me go back to C, right? So when I cover this edge from B to D, B to D is how much? B to D. This edge is 34 actually, right? And D to C, D to C is 10. D to C is 10, right? So what is the tour I am actually generating? Let me show you, right? So we started with A, we went to B, so we took this edge, that is 20. From B to D, we took this edge, that is 34. Okay, fine. D to C, I took this edge, which is 10. So I took this edge. Now I'd see what cost I should return. I should return the cost of going back to A. Right? From C to A, how much is the cost? C to A. This cost is 42. C will return 42. What is D is going to return? It is going to return 10 plus 42, that is 52. What is B going to return? It is going to take the minimum of the two paths we are getting, right? So I can go A, B, C, D, A, or I can go A, B, D, C, A, right? So this path is A, B, D, C, A, right? So these are the two paths that I can generate from the branch that is starting with AB, right? So we are in the branch that is starting with AB. So these are the two paths. So in the first branch, we were getting a cost of 85. Now we are getting a cost of how much? So this is 42 plus 10, 52, 52 plus 34. It's going to be 86. So it's going to take minimum of these two, right? So from here I was getting 65. From here I was getting 86. The minimum is actually going to be 65 and 86. It's going to be 65 only, right? So B is going to say that, okay, if you start with AB, the minimum tour cost of the remaining tour is actually going to be 65, right? This cost is going to be 65. In a similar way, you're going to backtrack, you're going to come into this direction. When you're at A, again it is 001. When you're at A comma C, when you're in this branch, you're saying that fine, from A I will go to C. I will go to C first. So this edge is 42. Then you can say, okay, the visited array looks like this, 0101. That means B and D are not visited. So I can go to B or I can go to D. Again, I have two directions. I can go to I can go to D, or I can go to uh so A, C, B, D, right? Yeah, this is what it is. And here I can say, okay, I can go to B also, right? This will be another two, right? And similarly here, you can say, okay, I can go to so here it will be like A and D have been visited 1001. I can go to B or I can go to C. So if I go to B first, it will be 1011, or I can go to D first. So it will be or I can go to C first actually. It will be 1101, right? So from here, I know the only node left I can cover here is C, and here the only node that is not covered is B, right? So if you look at all these branches, you're actually getting all the permutations, and of course from all of the answers that you're getting, you have to take the minimum, right? So maybe from A, if I go to B, I get some answer. I go to C, I get some answer. I go to D, I get some answer, right? And recursively I have to take minimum at each stage, right? So this is going to give me the minimum cycle tour, right? So what are the tours I'm going to generate? I'm going to generate A, B, C, D, this branch. Then I have A, B, D, C, this second branch. Then I have A, C, B, D, third branch. Then I have A, C, D, B, the fourth branch. Then I have A, D, B, C, fifth branch. then I have A, D, C, B, the sixth branch, right? So you can see I'm getting all the 3 factorial permutations of this part, and of course the tour will be ended at A, right? This part is something we will hard code in the base case. Base case we will handle, right? That okay, if you hit the last node, if you have covered all the n nodes, do return the cost from the current node to the source node, right? So this is something we will cover. So this way we are going to generate all the tours. Of course, the complexity looks like we are exploring n minus 1 factorial options, right? You can do n factorial options also, but you're going to get the same result, right? So why spend n additional time, right? And n into this time, right? So again, this is not good. Uh, this is a very actually huge time complexity, right? Huge time complexity. It's factorial. It's going to increase exponentially, right? This is like a exponential complexity, right? But that is a brute force algorithm. But we'll try to optimize it a little bit. But first, we will write the code for this algorithm, right? So what we need to do, we need to use the concept of backtracking here, right? And we need to calculate the tour cost, right? So what I can say about the recursive relation, I can say fine that from the current city, okay, from the current city, the cost is going to be, let's say this city connects to a particular neighbor. So let's say this is city. This connects to some nodes which are not yet visited. So I can say the cost of this edge, okay, plus let's say this is the neighbor node, right? So the cost to do the complete tour from the neighbor, right? And this will be minimum for all unvisited neighbors, all unvisited neighbors, right? So I take this path, some cost is I'm getting some answer A. I take this path, I'm getting some answer B. I'm getting some answer C, right? So out of all the 3 options, I'm taking the minimum, which is like here also, right? So that is something I am going to do. This will be my kind of a recursive relation, and the base case is that if I have visited all the cities, right? So if I have visited all the cities, right, I have to return the cost, that is the edge cost, from the current city where I am. If I'm at D, I have to return the cost going back to A, that is my source node, right? Or if I'm at C, I have to return the cost from C going back to A, right? It depends upon what is the current city, the source will be always A. This will be kind of my base case, right? So I hope you got a high level idea about the algorithm. With implementation, it will become little more clear. Let us jump into the code and see the implementation of traveling salesman problem. So I'm going to make a method which is going to return an integer. Let me call it as min cost tour. Right now I'm going to write a recursive method, which is also the brute force implementation, brute force approach that we have just discussed also, right? So what are the parameters I will accept here? So I'll accept the adjacency matrix. So I've already created this matrix. So I know the graph, which is this distance matrix, and then I will need to maintain what nodes I have visited so far. So it will be a Boolean array called visited. Then I need to know at what node I am currently at, and maybe how many nodes are there in total, right? Let's create the visited array also. So Boolean visited. Let me do it here. So Boolean visited. This is equal to new Boolean with n nodes, and initially I can say everything will be set to false. Okay. We'll see. If we need anything else, we'll add the parameter, right? So what is the base case? Okay, I also need to know what is my starting point, right? So here I'm assuming it is the 0th node, right? Either you can take input or you can just assume it to be 0. So we can say, okay, it's going to be the 0th node, right? So then I have to write the base case, and then I have to do the recursive case, right? So we are assuming that the source node is always 0, right? Is always 0th index, right? So here A is going to be my source node. So ABCD, right? So number of cities. So base case is I have explored. Okay, one more parameter I need to note is how many cities I have visited so far. So that is the count, right? So one way to check it is that if all the cities have been visited, that could be your base case. Or you can maintain a count that, okay, if my count is, let's say 4, that means I have visited all the 4 cities and I am now in the base case, right? So that could be one way to check. So if my count equals n, that means yes, we have visited all the cities, and what we have to return from the base case is the cost from the current city to the zeroth city, right? So I can say return the distance from the current node, maybe it is 3 or 4 or 2 or whatever, to the zeroth node, right? Because 0 is, we are assuming it is the um, starting point, right? In the recursive case, what I have to do is the first step, because I'm visiting a city, in the first step I will mark this node as true, right? Okay, yes, we have visited this node. Then we will iterate on the neighbors, right? So we'll see what are the neighbors that the current node has, right? So everything is a neighbor, right? For int I equal to 0, I less than v, I plus plus, right? Now because it is a adjacency matrix, I have to iterate over all the edges, and then I have to check what nodes, what cities not have been visited, right? So I can say, okay, fine, the neighboring city is, I just call it neighbor city, uh, is going to be I, right? What is v here? V is the number of nodes, which is n, right? So I can say, okay, fine, if not visited, what is the neighboring city? The neighboring city is I, right? So if I is not yet visited, we can calculate the cost, right? So we can say, okay, fine, what is the cost? So that is going to be the distance going from the current city to the ith city, right? Plus the remaining cost. So that will be minimum cost tour. Uh, Given the distance array, given the visited array, the node is now going to be I, the count will be count plus 1 and n, right? So what I'm trying to say is that you are at a particular node, right? You can go to some ith node, right? So I'm trying to calculate what cost this node should return. So I'm saying this cost, that is distance from node to I, plus recursively the cost to complete the tour from this ith node. So in the base case, when I visited all the cities, when I'm at the last city, right? So I say, okay, I'm adding the cost of this node to 0. So at this node, I return the cost from going to this node to the 0. Basically, this cost I add here and I return this, right? Something like this. Now this, I don't have to, I have to take the minimum also, right? So from here, I can go to many places. What I will do, I will take minimum of all, right? So whatever branch gives me the minimum, I will take that minimum, right? So what I can do to do that, so I can say, okay, here let's assume the answer is integer dot let's say max value. The answer is very huge, but here I can say answer will be always minimum of cost comma answer, right? And here I can say return answer. So what I did, I took a variable called answer and I said, okay, let's compute this cost C1. So whichever is minimum will be updated in the answer. So answer is maybe now C1. Let's compute this cost C2. Maybe if this is minimum, it will be this cost C3. Maybe it is higher. Maybe this cost C4, this is higher. So maybe C2 is something that I will return from this node, right? So this function will be math.min. Okay. So I think this looks like a good implementation of the recursive function that we have discussed, but we have missed one important step, right? What about backtracking, right? So when you're coming to a node, you're marking a node as visited, right? So when you're going, okay, I'm at A, I want to go to B, I want to go to C, I want to go to D, right? So here your visited array looks like 0, 0, 1. Here it looks like 0, 0, 1, 1. Here it looks like 0, 1, 1. Here it looks like all ones, right? But now you're going back to C, so it should get restored to this. You're going back to B, it should be like this. Then you're going back, you're coming at D, so it will be 1, 1, 0, 1, right? Then you're coming at C, it will be 1, 1, 1, 1 again, right? So you have to do that. Okay, I'm going back from the current node, so visited of node will be false. So that is my backtracking step here, right? So now let us test our code. So I am going to call this function sout min cost tour given the distance array, then given the visited array, then I have to give the node. So starting node is 0. Okay, count. So I'm counting 1, 2, 3, 4, right? Either you can count from 0 to n minus 1, which is also fine. I'm counting 1, 2, 3, 4, and the number of nodes is 4. That is also fine, right? So let's try to run this code and see what output do we really get. So we are getting an output that is 85, which is actually the correct answer for the given problem. And that tour is nothing but that tour is A, B, C, D, A, right? So this is 20 plus 30 plus 10 plus 25, right? So if you try out any other tour in this graph, you will get a value that is actually higher than 85, right? So I hope you have understood the brute force algorithm, and this is something exactly same what we did in the theory as well. So you have seen the recursive implementation, which we said that it has a n minus 1. We are computing n minus 1 factorial tours, and this will be the complexity of the current algorithm that we have discussed, right? Now this algorithm can be optimized a little bit using dynamic programming. First of all, we need to see why it can be optimized using DP, right? So the need for dynamic programming and how it can be used, right? Now suppose there is a tour, right, that starts with A, right? And then maybe I cover some nodes, let's say B and C, okay? And in some other branch, I cover the nodes C and B, right? Now it is possible that I have three more nodes. I have D, E, F, okay? And the same sequence of node is also here, D, E, F, right? When I'm making a recursive call, what I'm doing, I'm saying, okay, let us compute the cost starting with D and covering nodes E and F and going back to the source node, right? So this cost will be, let's say, X, right? This cost will be A. So this cost is, let's say, C1, right? And can I say in this branch also the same cost can be reused, right? The same cost can be reused, right? So what I'm trying to show is that these two branches, they will have different answers, right? Because here you're covering A to B. Maybe the cost is some cost AB, right? And here the cost is BC, but here the cost is AC, and here the cost is CB, right? So what I'm saying is that the total cost of branch B1 is going to be AB plus BC plus cost C1, right? And in the branch B2, which is this branch, the cost is going to be the cost of AC plus cost of CB plus the cost of this, maybe, right? So of course it can be calculated in an optimal way, whatever is the optimal cost, and I am assuming that DEF is the most optimal order for this problem, right? So maybe this cost is again C1, right? So what you can see here is that there are overlapping sub problems, right? There are overlapping sub problems here, right? So if there are overlapping sub problems, and of course there is a optimal substructure where we are combining multiple sub problems, where we are uh, computing the answer for this problem by reusing the answer from the sub problems, right? So hence it becomes a problem of DP, right? Now we talk about, okay, if it is a DP problem, we want to memoize something, right? We want to memoize something, right? So what is the state of DP, right? How do I decide like what to do, right? So at this point, one thing I need to know is that, fine, I need to know what is the set of cities I have visited. That is like one thing, right? So if the set of cities I have visited is different, then the two problems cannot be same. Okay, if you have visited ABC, you have visited ABC, then it is the same set of visited you have so far, and here is the set of cities that are not yet visited, right? If set of cities that you have visited is something, right? And secondly is at what what node you are currently at, right? See, if I change my current node, right, my answer is going to change, right? So if it is you are at C, you want to go to D, this will be some cost CD. If you are at B, you want to go to D, this will be some cost BD, right? So basically what I'm trying to say is that um, you have to calculate an if I show you the recursive code first, right? So let's see the recursive code, right? What is actually changing in this code, right? When you're making the function call, one thing that is changing is the node. Node is becoming a neighbor, right? And second is the visited array, that is also changing, right? This count is something we can easily maintain, right? This n is fixed, this distance is also fixed, right? This distance is also not changing. So there are two parameters that are changing, and if these two parameters are changing, our answer is also changing, right? So that is something I'm trying to tell you, that my function is dependent upon these two parameters, right? So that means my DP table is also going to be dependent upon these two parameters. So my state of the DP will be DP of visited comma node is going to be some answer, right? This is going to be some answer, right? So I hope, I'm assuming that you already know DP, right? But now the thing is, if you are making a 2D DP table in which you are going to store set of cities that is visited, this itself is an array, right? How can I use an array as an index? This is a problem. This is something we need to think, and that is where the concept of DP with bit masks will come into picture, right? DP with bit masks, right? So what I'm going to say is that we are not going to use this DP array or visited array. Instead, we are going to create a mask that is going to act like a visited array, right? So I will show you that how we can do it. Let us talk about DP with bit masking approach for this problem. So what we are going to do now is we are first going to convert this code into a bit masking based code, right? Basically the idea is we have the same logic, but now we are not going to make a visited array. Instead, we are just going to have an integer that represents what set of nodes have been visited. So in the beginning, this integer will be 0, right? 0 means all bits are actually 0, right? And if you visit node A, right, you can simply set this bit 1. Then if you visit B, you can set this bit 1. You want to visit C, you can set this 1. You can visit D, you can set this 1. Then if you backtrack, right, so integers are created locally in the call stack. So that means from this A, you were going to B, you were going to C, you were going to D, right? So this was 0001, this was 0011, this was 011, this was 111, right? From this branch, you go back. So integers, since they are created locally in the call stack, this is a copy of this one, right? So you do not need to write explicit backtracking code, whereas arrays are shared, right? Here it is an integer, so it's going to backtrack automatically. From here you go back, it is going to backtrack, right? And how do I check whether a particular integer was what set of cities have not been visited, right? So at B, this number, this mask is showing like this, right? So you can iterate in this direction over the bits, and then you can see, okay, yes, this bit is not visited, so you made a call on C, right? But when you came back, you said, okay, next call I will make on this, right? So you can visit D, right? So this mask will look like 1101. So basically there are two things. One is you need to check what cities have been visited or not, so you have to check ith bit, right? And once, if you want to visit that city, you have to set ith bit, right? So that we will do in the function call, right? So here we have we don't have an integer array now, we have a visited, right, which is normally and simply an integer. So I'll call this method as min cost tour bit mask, okay? So recursive case, this I don't know, this I don't need setting the visited array, because for the 0th city I can do it directly from the main, and for other cities I will do it in the function call, right? So I will update it here, right? I will update it here, right? So visited I will update here, and if not visited I, now since it is not an array, what we need to do, we need to use the bit masking logic, right? So let's see how we can do it. So I can say, okay, fine, so I can do one left shift I, and I can do a and with visited. So if this value is 1, or if this value is 0, then it means the city is not yet visited. What is the error we are getting here? Required type boolean, provided type int. Okay, I think the bracket is mismatching here. This will go So I have fixed the brackets. Now how do I check, right? So basically for this, let's say I'm at this particular state and I'm running a loop from 0, 1, 2, 3, right? So maybe the value of I is 2. What do? I say 1 left shift I, 1 left shift 2. So that is 1, 0, 0. I'm doing a AND with this, right? So if I do a AND, what do I get here? I get all the bits which are 0. So basically I get the value of this bit. So if this bit is 0, that means the ith city is unvisited. If it is unvisited, I can visit it, right? So I can give the distance array and I can update this bit to be 1. So I can say, okay, this can be updated by doing a OR with this value, right? So this is my mask that I've created. If I can do a OR here, this bit will be set, right? So using AND, I can check ith bit is set or not, and I can set the ith bit by doing a OR with this. So I can say visited or 1 left shift I, right? So this visited will be updated here. So I can say visited or 1 left shift I, right? So that is my visited array. Then what else I need to give, right? Okay, so this call will be minimum cost to bit mask, right? Now backtracking is not needed. I told you it will happen automatically, right? So basically I'm converting that code into a bit mask based code. So we have done it. So here we are checking by using the concept of bit mask whether a city has been visited. If it is not visited, I visit it. I set that city to be visited right here. So in the beginning when I'm making the call now, so what I will do, I'll say okay, s out min cost to bit mask. I give the distance array. I give visited. The starting node is still 0. The value of visited is 1 because A is visited now, and number of count is still 1. The number of node is still 4, right? Nothing changes there. Okay, so visited will be 1 in the beginning, right? Visited is 1, node count and n. This is 4, right? So I give 1 additional value. So I think this looks fine. Let us go and run our code, right? Basically it is the same code. Now we are doing it without using the visited array, so that we can use visited as a state inside our DP logic, right? So you can see we are still getting the answer 85, right? So I hope you have really understood this one as well. Nothing has changed. The way we check visited, that has changed, right? And the way we set visited array, that has changed, right? Since I'm passing a value, right? Passing an integer by value, right? That means when we are doing backtracking, that integer will automatically recover the original value, right? So if you go down and you come back, so if it was 1 1 triple 1 0 and here it was 1 1, when you're going back it will automatically become triple 1 0 triple 1, right? So explicitly we don't need to write the backtracking step which we have done here. And the reason of doing this is that I don't want visited to be an array because I want to use it as a state inside my DP computation, right? So that was the motivation for changing it to the bit masking logic. So right now it is recursion with bit masking, right? Now one final step is left, that we need to use memoization, and we saw that there are overlapping sub problems. So let us change this code into a DP based code. So let's add the touch of DP to our bit masking code, right? So I'm going to use top down DP because we have already done the recursive implementation. It's going to be pretty easy now. So in top down DP we need to create an array for memoization part. So as I discussed that my answer depends upon two things. One is visited and one is node, right? My node can take a value between 0, 1, 2, 3. So I have basically 4 nodes, and my visited can go from 0, 0, 0 to 1, 1, 1, 1. Basically I have here 16 states. Basically I have 2 raised to the power 4 different states, right? So my DP array will be of the size 2 power n followed by n, right? And of course this will be also my time complexity because I am computing each state exactly once, right? So now how do I make this? It's pretty easy. So I already know n, right? So n is already known here. So I can create a DP array. So I can say, okay, int DP of 2 power n is written as 1 left shift n, that is 2 power n, followed by n, right? So this, sorry, we will have to do it like this. This is equal to new int of this particular size. In the beginning, I can set this array. I can say, okay, everything is not computed. So I can set everything as -1. And in my bit masking code, I can add the touch of DP. So I can send this array. This function should receive the DP array as the next parameter. And here I can check that if a particular DP state is already computed. So if DP of visited comma n node is not equal to -1, that means we have already computed the state, so we can return the answer. So return DP of visited comma node. Okay, so I'm assuming that you have already studied DP, so I'm directly using DP without explaining much here. So DP of visited comma node will be equal to answer, right? So these are the two changes that we generally do in the top-down computation, and we also have to pass the DP array here, right? Now this will bring down the complexity from n minus 1 factorial to 2 power n into n, right? I think the code looks correct. Now let us run this code and see what we are actually getting, right? So we should still get an answer that is 85. Okay, we got a exception here. And I think it is because of arrays.fill will not work on a 2D DP array. So maybe let's initialize it. Let me simply put a loop for int I equal to 0, I less than 1 left shift n, I plus plus, and then for int j equal to 0, j less than n, j plus plus, I can say dp of I j, this is equal to -1, right? So I'm hoping that it should work. Yes, this time it is working. So that looks good. So nothing, no major change in the code. We simply added the code for memoization in our bit masking approach. And now I hope you clearly got a reason that why visited array should be a bit mask, why it should be an integer, right? Because we can use it in the memoization very easily, right? This I have changed, and this part I have. If it is computed, we return it. If it is not computed, we compute it and we store it before we returning. Rest of the code, there is no change here, right? No change in the here and no change in the base case. Base case is also same, right? So that's all for DP with bit masking. That was all for the traveling salesman problem. I hope you gained a lot of knowledge from this tutorial. So before you leave, make sure you hit the like button and share this video with your friends. Hello everyone. Today we are going to talk about the most talked algorithm in the graph theory. That is Dijkstra's algorithm. And it is the algorithm that is responsible for finding shortest paths from the source to a given destination. But before we get started, make sure you check out free masterclasses on Scalar's event page to learn from some of the best industry experts. The link is in the description below. Alright, let's dive right into the tutorial. So what is Dijkstra's algorithm? It is an algorithm for finding shortest paths between nodes in a weighted graph, which may represent, for example, road networks. For example, you're traveling through a cab and you want to find out what is the shortest path to reach some X city. And this is where Dijkstra's algorithm will come into picture. So it was invented by computer scientist Dijkstra in 1956, and it has many other applications as well. This algorithm actually exists in many variants, and the original algorithm found out the shortest path between two given nodes, but we will do a more common variant in which we will build this algorithm as a single source shortest path algorithm. That means starting from a single source, it will find out the shortest path to all other nodes in the graph, thus producing a shortest path tree. So input of this algorithm will be a weighted graph and a given source node. And once you have this as input, let's say the source node is A, the goal of this algorithm would be to find out what is the minimum distance in which I can reach every other node of the graph, right? So for example, what would be the minimum distance to reach B, D, F, E, and C, right? So in the beginning, we can say, okay, the source is at 0. and we want to compute the shortest distances to all other nodes. This is what we will do in this algorithm. That is why it is called as single source shortest path. So we will be doing this. Starting from a single source, we will be finding out shortest path to all other nodes in a weighted graph. That is important, right? So if the graph is not weighted, if it is an unweighted graph, then we have already seen that a simple BFS can give us that thing. But if the graph edges are weighted, then this is where Dijkstra's algorithm will come into picture. So let us go and build this algorithm, try to understand the intuition and the logic of this algorithm. Let's see how this algorithm works. So we will start from the given source node. So let's assume that we are given this weighted graph and we are given, okay, the source node is, let's say, A, right? It can be any node, but I am assuming in my scenario the source node is A. What I will do, I will initialize the distance of the source node as 0 because this node is at distance 0 from itself. So what we are going to do, we are going to maintain a distance array and we are going to say, okay, there are different nodes A, B, C, D, E, F. So what this algorithm does, it initially gives an infinite distance to every node except source node. So all the nodes except the source node, they are not yet discovered. So they are at infinite distance. So that means they are not yet discovered. So B is at infinite distance, D is at infinite distance, E, C, and so. And distance of the source node is going to be 0, right? What do? You do something like BFS. Of course, will pick this node. Now, this node is having the minimum distance. Okay, so it makes sense. So out of all the edges, if you have to pick some edge, will you pick this edge B to D? The answer is no. Will you pick D to E? No, because D is at infinite distance, E is at infinite distance. So what is the first node you will pick? That node will be A. So this algorithm is also a greedy algorithm. So that means we will always make a choice that looks best at the moment. But at this moment, the choice that is looking best is A. So what I will do, I will pick A, okay, and I will try to cover the neighbors of A. The neighbors of A are B and they are C, right? Now, if I pick this edge, can I go from A to B? The answer is yes. If I pick this edge, the distance of B, which was infinity, now this distance will become 4. Yes or no? The answer is yes, it will become 4. The distance of B will be how much? So from A, I will update B, and of course I can take this edge and I will update C also. I will update C also. Okay, so distance of C, which was again infinity, it will be now 0 plus 5. That will be, this distance is 5, and in the array also we can update that this distance is 5. So what I did, I picked A and I put it in some data structure. Okay, so I have some data structure. I will tell you what this data structure would be, right? So we initially put A and then we said, okay, we picked A from this data structure and we updated B and C. And now I want to do this step again, right? Now I cannot pick A, but I have to pick again something, right? Now I'm going to put B and C in this data structure. Why? Because B is at a distance 4, right? Okay. And I want to put C also. C is at a distance 5, right? These nodes are also inserted into the data structure. Now, one property of this data structure we would require is, since it is a greedy algorithm, we want this data structure to always give us a node with the minimum distance. So right now you see this node which is at the front of this data structure. Okay, so something like a min priority queue, right? Or something like a ordered set, right? This data structure can be min priority queue, it can be set also, right? Now what is the next node I'm going to pick? So A has done its work. I cannot traverse any other neighbors from A. So what I'm going to do now, I'm going to pick B. Okay, and of course B's distance cannot be minimized because I don't have any other node which is having distance less than B. So B cannot be minimized. So B is now having the minimum distance out of all the nodes that I have, right? So now it obviously makes sense to pick B. So that means B is now out. I cannot update B any further and I can update the neighbors. So what are the neighbors? So one neighbor is C. So can I pick this edge? Can I travel this edge? If I go via this edge, you look at that, okay, if I try to update C, the distance of C which was 5, now it will become distance of B, that is 4 plus 11, 15. So it is increasing, so I do not update it. So I do not update C, right? Then I talk about this edge, B to D. So D was at infinite distance. Now the distance will be 4 plus 9, that is 13. So is it getting lesser? The answer is yes. So I updated. This distance is 13. Okay. So this distance of D is going to become 13. And of course, I'm going to push 13 comma D in my data structure. 13 comma D is in the data structure. What about this edge? Can I take this edge? The distance of E, it is how much? It was infinity. Now it is 4 plus 11. 4 plus 7, that is 11. Distance of E is also getting updated. So it was infinity. Now it is becoming 11. And I'm going to insert this into my data structure, right? So I want this to be in a way that is sorted according to distance, right? Because in future it might happen that from E to D there is an edge which is going to minimize this D, right? So we want to pop E first, right? So distance of E is actually how much? It is 11 comma E, right? So this distance infinity it should be 11, right? This should be 11. Now this should get inserted somewhere here, right? So let's say I now my data structure looks like this. So I have 5C followed by 11E followed by 13D, right? Something like this. Because B is now already out. This is how my data structure is going to look like. Now, next thing that I'm going to pop is I'm going to pop out C, because now all the nodes that I have traversed so far, this node is having minimum distance after A and B, and B has already visited this node, right? So we could not minimize this distance. That means C is at a minimum distance of 5. What I'm going to do, I'm going to now pick C, right? So we'll pick C and we'll try to update the neighbors, right? So neighbors which are not yet visited. So A and B, they are already out of the queue. So we will not update A and B. We might try to update E, right? From C I can go to E, right? So I can go to E. So E was at a distance 11. Now E is at a distance of 8. That means, yes, I need to update the distance of E because it is getting lesser. This distance will become 8, and now E is also in my data structure. E is also here, right? So if it is here, what should I do? I should update it, right? I should update it in the data structure also, right? Now, if you're using something like a min priority queue, right, then you do not have this update operation built inside priority queue, right? So instead of using a min priority queue, what we can do is we can use a set, right? Something like a tree set that keeps things ordered, right? In C++, you can use a set. In Java, you can use a tree set, right? This data structure will be set. Why? Because set also does not allow updation, but it allows you to remove and insert any element. So set allows you to do remove and then you insert, right? What I'm going to do, I'm going to remove this pair 11e. So this is already popped up because we have picked C. And now I want to update 11e, right? So I cannot update directly inside the set. What I can do is that E which was at 11 distance, I want to say this distance would be 8, right? So I'm going to remove this and I'm going to insert 8 comma. This is how I can update it in the set. And set it is an ordered set. 8 is lesser than 13, it will be present here, right? Then any other edge? No, I don't see any other edge, right? Now E, it is at distance 8, right? Now next node that you will pick is you will pick E, right? You will try to update the neighbors which are not yet covered. One neighbor of E is F. So F is at infinite distance. Now this distance will be 8 plus 6, that is 14. So F distance will be 14. So you can say, okay, F is now at distance 14. And of course you can put it into the set also, 14 comma F. So you took this edge. Then E can also visit D. D is not yet visited. So it will be now 8 plus this 13, right? So 8 plus 13, which is how much? Which is actually more. So you will not update D, right? So it is 21. So it's already 13, so you will not update it. That's it. So E is also done. So we are done with E. Then you pick D, and then you can think, can I update anything? So the only node that is left in is F, right? So I'm going to update the neighbors. So E is a neighbor, B is a neighbor, but they're already visited. They are out of set. So we are not going to touch them. And I'm going to say, okay, let me pick D, and I will try to update F. Update F. So now this distance is 13 plus 2, that is 15, but F is already 14. So you do not update it, and that means we are done, right? So if you try to analyze carefully, what happened is, I'm just going to remove these edges, and we'll try to highlight, right? So we'll what we will get a tree like structure, right? From A we went to B, from A we went to C also, from C we went to E, and from E we went to F. So 5, 3, 8, 8 and 6, 14, right? From B we went to D, and that's it, right? So if you look carefully, the distance of A is 0, the distance of C it's 5, the distance of E it is 8, the distance of F is 8 plus 6, 14, right? And then from A to B, this is how much? This is 4, and from B to D it is 13, right? So this is actually the shortest path to every node. Now, if someone says, okay, give me the shortest path from A to D, you know this path is going to be 13. A to F, you know this path is going to be this much, right? It is going to be 14, right? So, although I hope you are getting it, right? So, this is what this Dijkstra's algorithm is. And as we discussed, it is a greedy algorithm because it is always picking the node whose distance is minimum. For this, we will use a data structure like set, and instead of having a queue, we will have a set like data structure from which we will be picking out these nodes, right? If you want to travel the path, what you can do, you can create one more array like distance, that will be the parent array. So for every array, whenever you are updating the distance, you can also update the parent. For example, parent of B is A, parent of C is A, parent of E is C, parent of F is E, right? So if you know the parents, you can easily backtrack and trace the path also, right? So this is how you can get the path and the distance. Now we will look at the code implementation of this algorithm. Let us talk about implementation of Dijkstra's algorithm, and I will show you what I am going to do. So I already have some boilerplate code, which is the code for creating a weighted graph. So in this weighted graph, the representation I'm using is adjacency list. Adjacency list is an array in which each object is a linked list. So there are v number of linked list. Okay. So if the graph is like this, 0 is connected with 1, and 0 is connected with 2, 1 is connected with 3, and let's say this edge is 4, this edge is 5. So in the adjacency list of 0, that means at the 0th position in the array, I am storing a linked list in which I am pushing pairs. So it is weight followed by edge. So it is 4 followed by 1. Then 0 is connected with 2. So I'm storing 5, which is the weight followed by the node, which is 2, right? Similarly, 1 is connected with 0 and it is also connected with 3. I'm storing, okay, the weight is 4, the edge is 0, the neighbor is 0. Similarly, this is, let's say, x. I'm storing x comma 3 and so on, right? So this is how my adjacency list has been created. So to do that, I have defined a pair class in which I have two integer values, one for the node and one for the edge weight. Okay, so this distance here is representing the edge weight, right? The distance between two nodes, right? Now here we are going to build our algorithm void Dijkstra's, and I'm just going to get the source node because this method I'm defining inside the graph class, so it has access to the adjacency list that is already there, right? So we don't need to pass adjacency list explicitly, right? Now before I actually write the algorithm, I would like to show you how tree set in Java works. Maybe some of you are not familiar with how to create a tree set. Okay, so tree set is a ordered set that stores data like in a sorted order, right? So let's discuss about tree set first. Let's create a tree set object. So I can say tree set, which is of the type, which is going to hold objects of the type pair weighted. So pair w is my class, and let's me call it as set. This is equal to new tree set, and I'm also going to define a lambda function so that this tree set knows that I have to sort objects according to the distance property, right? So basically in lambda function you define like this. So you have the bracket to hold the parameters. So maybe I'm going to get two pairs, pair WP1, pair WP2. Basically I'm going to define a criteria that okay, sorting should be based upon distance, and here I'm going to the return value, so that is going to be P1 dot distance minus P2 dot distance. I think we would require round brackets here like this. Now I can insert few items here, so I can say okay, s dot add maybe a new pair W, and I can give some distance, maybe distance is 5, the node is let's say 11. Okay, then I can add s dot add new pair. I can set the distance is let's say 3, the node is 15, right? And I can say okay, s dot add new pair. So I'm just hard coding these values so that I can show you how this actually works. Then the distance is maybe 8 and the node is let's say 7, something like this. Now I want to remove nodes from the set in a way the node with the lowest distance is removed first. So I should be able to remove 3, then 5 and then 8, right? So how do I extract those nodes? Let's see. So while my set is not empty, what I'm going to do, I'm going to simply poll the node which is at the beginning. So I can say s out s dot poll first. So it's going to give me the pair. So I can just print the distance. That should be now in sorted order, right? So let us run our code. So I've created a main function, and this is going to be let's say static void, not static void, void Dijkstra. Let's make it public. We can call, I think there is a spelling mistake. The method I've called it as Dijkstra, not Dijkstras. So let's run this code, and what we can see, we are getting 358, right? So that means we are getting data in a sorted order. That is the expectation. So that means this is working fine, right? Okay, one more thing, just like add function, we also have a remove function in the set. I can say okay, I want to remove a pair which is let's say 5 comma 11, right? This is pair comma pair W. So if I go and run this code, you will see in our output we will not get 5, right? So we are getting 3 and 8 only, right? So we are getting 3 and 8, but if you give some pair which does not exist, let's say 15 comma 21, now this pair does not exist in the set, so this remove function will not do anything, right? So it's not going to throw any exception. That means we can still remove this, we can still use this, right? Now this thing I will be using while building the Dijkstra's algorithm. So I hope you have understood how do we work with tree set. So here I have defined the tree set object, here I have defined the comparator, then I added few items in the set, then I removed some items using the remove function, and then I printed. When I'm doing poll first, it is going to give me the smallest item first, and from that item I'm just printing the distance property of that item, right? So I hope all this code is clear. Now we will jump into the actual algorithm and let's see how we code it. Let's start implementing the extras. So first step would be I would create a distance array. So int distance, this is a new distance array, and I want to set everything to infinity. So I can use arrays.fill this distance array with integer dot max value. Okay, and the distance of the source node should be set to 0. So distance of source will be 0. Now my set is created, my distance array is created. I can actually start doing the traversal, right? So in the beginning, what I can do, I can push my source node into my set. So I can say okay, s dot insert, sorry, s dot add, and I can create a new pair with the distance of the source node which is 0, and the second item will be the source node. So that is going to be source, right? While I can say okay, my set is not empty, I want to extract this pair, right? So the pair we will get will be 0 comma source, right? So in the beginning we are going to get this pair. So I can say okay, pair W P, this is equal to s dot poll first. Now from this pair I can extract two things. So one is my current node, which is p dot node, and one is going to be my current distance, like how much distance I need to travel to reach the current node from the source. That will be p dot distance, right? So that will be actually distance of, so distance is Now you don't need to confuse here. So distance we are storing in the distance array. Okay, so p dot distance, that is fine. Okay, we have pushed, that is also fine. P dot distance can also be used, right? So right now this distance, I know it's going to be updated in the distance array, so I'm just saying distance of source node. Right now I need to iterate on the, sorry, not source but of the current node, right? That is the distance of the current node. So basically distance is stored in two places. One is in the distance array and second is in the set. Now what I'm going to do, now suppose I removed this node 0 and it is now connected with some other nodes, right? Maybe 1, maybe 2, right? So these are right now infinity and this distance is 0. So I got this node 0 0, right? So I can say, okay, let me take this edge, and maybe this is 4. Let me take this edge and let me try to update the distance of this node, and let me try to update the distance of this node if it is getting smaller, right? So how do I get, so I can say for every pair w, that I can say, okay, p that belongs to adjacency list of current node. So I am going to iterate over the adjacency list of the current node. So I think, let me check what is the property here. The property is adjacency list, fine. So it should be fine. So let me call it as neighboring p. So the neighboring pair. So neighboring pair. Yeah, I cannot reuse the name p here. So it will be neighboring pair. So I can say, okay, the node is neighboring pair dot node, and the edge is nothing but neighboring pair dot distance, right? Now how is this adjacency list created? So it is created like this: 0 is connected with 1 which is at distance 5, which has this edge length 5 and the node is 1, and this edge length is 4 and the node is 2. So this is what is my neighboring pair. So neighboring pair is this, getting the node which is this, I'm getting the edge which is 5, right? Now you have to see that if you take this path, if you go from 0 to this node, right? Let me say this is 8. Okay, let me say this is 8. That will be better actually. Not this one. This is 8, right? So 5 comma 8, and maybe this edge is 2, right? This edge is 2. Now I will show you what is going to happen. So you are going to iterate over this. You're going to say, okay, distance of 0 plus 5, is this less than infinity? If it is less than infinity, you should update it. So you can say, okay, if the current distance which is 0 plus the edge that you are taking, is it less than the node that you are reaching? So that node is 1, so distance of that neighbor, let me call this as neighbor only, right? So you're reaching a neighbor. If the distance of neighbor is getting minimized, you should minimize it, right? So two things I'm going to do. Now here we have two possibilities, that this node was already present in the set or this was not present in the set, right? What I'm going to do, if it is present, I will update the distance. If it is not present, I will simply add it to the set, right? Now update operation is not possible on set. So in order to do an update, I can say, okay, I will do remove plus insert, right? That is how I'm going to do it, right? So what I'm going to do, irrespective of it is present or not, I can always call the remove from the set, right? So removal can be done if even if the element is not present, nothing will happen. If it is present, it will get removed. So update, what I'm going to do, I'm going to say, okay, let's remove the old object from the set. The old object is going to be a pair, which is going to have two things. One is the distance, like the old distance. So that will be distance of the neighbor followed by the neighbor. You can remove it. Now, if it is present, it will get removed. If it is not present, nothing will happen. So we can execute this operation. Then we can update. Okay, we can calculate and the new distance. The new distance will be nothing but you can say the new distance is nothing but current distance plus edge. That is the new distance, and where it should get stored at two places. One is in the distance array. The distance of neighbor you can update in the distance array, and here you can say, okay, I have to add it to the set so that in future it can update its neighbors also. So I can say, okay, s dot add new pair where the distance is now distance of neighbor. Now this is the updated value. Look at this. This is the updated value, whereas this is the old value, right? So I've updated it and I've pushed it into the set. Fine. This looks good. If we keep on doing this, current node, I've used it here. Fine. Current distance, I used it here. Fine. This looks good. I think this is done, right? So finally what we can do, we can print the distance array, right? So I will do the dry run, don't worry. Print the distance array. So I can say sout arrays dot toString. If you want to return distance of some specific node, you can return that as well. But here I'm just printing the distance array. Now let's go and run this code. So I'm getting 0, 4, 5, 13, 8 and 14. I will show you the graph for which we have done this. So this is the same graph that we have taken in the example. Let's see how we are doing it, right? So we are saying in the beginning distance of source is 0. So this distance is 0 and s dot add new pair. So in my set, I have a new pair 0, 0, right? While set is not empty, I remove this node from the set. So current node is 0, current distance is 0. So for the neighbors of this node, which are this and this 1 and 2, I say okay, neighboring node is this, fine. If I take this edge, that is 4. If it minimizes this distance, which is infinity, then I update it. So I remove a pair from the set which is this 1 comma infinity. So this was not there, right? Infinity comma 1, it was not there, hence nothing happens in this line. And I update the distance. So distance of neighbor, so this is my node, okay, this is my current node, this is my neighbor, right? So I update the distance of neighbor as current distance, which is 0, plus this edge, which is 4. This distance becomes 4 and I add it to the set. So I add 1 comma 4 in the, let's say 4 comma 1, I'm putting distance first. So I add 4 comma 1 in the set, right? In the same iteration, because this for loop is running, I also update. I take this edge and I say okay, this was infinity, and I add 5 so this distance becomes 5. So I add 5 comma 2 in the set, right? So it is sorted, so 5 will come here, right? This is gone now, right? So distance, this is gone from the set because we did pole first, right? Pole first will remove this item. Next item we will get is 4 comma 1. So we will get this, fine. We get the node which is 1, we get the distance, we get the current distance which is 4. Then we try to traverse the neighbors, right? So we try to cover this node, this node, this node, this node, right? Now from 1 to 0 if you go, distance will increase. So this if will not execute. From 1 to 2 if you go, again the distance will increase. So this if will not execute. But if you go from 1 to 4, this distance was infinity. So this will get updated. So this will be 4 plus 7, this will become 11. So what you will do, you will push 11 comma 4 here by taking this edge, and again this was infinity, so you will do 4 plus 9, which is 13. So you push 13 comma 3 here, right? So this is also covered, right? Now 1 has done its job, 1 is out. Next you pop this node, so you get this node and you try to update the neighbors. If you go to 0, distance will increase 1. If you go, distance will increase. So you take this edge, and how much you get? Now you get, okay, earlier it was 5, 5 plus 3, it is 8. So this was how much? This was 11. So this has to become 8. So what do? You remove this pair, okay, and instead of this you insert 8 comma 4, and of course this is removed. So 8 comma 4 is there. So next you will pick this pair 8 comma 4 and you will try to update the neighbors. So this will be 8 plus 13, this edge 21. Earlier distance was how much? So this distance was 13 actually, right? So it will be now 8 plus 13, which is 21. Hence you do not update here. But if you talk about this edge, so this was infinity, so it will be 8 plus 6, 14. So you insert 14 comma 5 in the set, right? So 8 is done. Then you pick this node 13 comma 3. You try to update this neighbor, which is 13 plus 13, 26. This neighbor increases, this neighbor, again this is 13 plus 2, 15, right? So again it is not able to update any node, so you remove this. So for loop does not run for the if condition is not true for this node, right? Then you remove this, again you are not able to minimize any of the neighbors, hence this is also gone, and hence you get the final distances. Okay, so you get 14 here. So the fifth node is 14. Then you have the fourth node, which is 8, fine. Then you have third node, which is 13, yes. Then you have the second node, which is 5, yes. You have the first node, which is 4, and you have the 0th node, which is 0. So that is the Dijkstra's algorithm for you, right? Now let us also talk about complexity in detail, right? So what about the complexity? So if you look carefully, how many times this while loop is running? So from the while loop, what we can accept that this loop is going to run how many times? Can you make any guesses? Or if you talk about these two loops together, right? The while loop and the for loop, right? So what is happening? In across all the iterations, what you are doing, you are iterating over the neighbors of a node, right? So if this is node, so in the adjacency list, if I have let's say two items here, I have 3 4 5 items here, right? 6 7 8 some items here, 9 items, 10 11 12, right? So what is happening? So what is happening, that in each iteration of while loop, you are iterating over neighbors of some node, right? So how many neighbors we will have? So it is basically, you can say I'm doing e iterations, right? I'm doing e iterations across all the iterations of this while loop, because we are iterating over the adjacency list, right, of some node. So across all the iterations, we are going over the adjacency list of all these nodes, right? So that means in total there are e edges. So hence there will be effective e iterations. And in each iteration, if we assume that this operation is being executed, right? So we are inserting or removing something from the set. That is not an order one operation. That is a log of set size. So how many vertices will be there in the set? So at max there will be v vertices, right? So that means in e iterations I'm doing an operation which is going to be log v, right? So the overall complexity is going to be e log v, and that is the optimized approach for Dijkstra's algorithm, right? Because if we are getting the minimum, we're getting the minimum here also. Pole first is log v, right? And this is also log v, right? So what I'm saying, that while and for loop combined, they are doing e iterations, because you're traversing across adjacency list, okay? And there are e edges, and for each of these iterations, you are doing an operation that is of log v complexity. Hence, the overall complexity of this algorithm is e log v, right? And this is the optimized approach for Dijkstra's algorithm. So that was the Dijkstra's algorithm for you. I hope you understood the algorithm as well as the code. Now this problem can also be formulated in the form of a 2D matrix. Given a 2D matrix where each cell represents the cost to travel through that cell, you might be asked to compute the shortest cost from a given source, which is some cell, to some other cell in a 2D matrix. You can implement the same Dijkstra's algorithm without having an explicit graph on a 2D matrix as well. So I am sure you will try it at your own. And before you leave, make sure you like this video, hit the subscribe button, and share it with your friends. I will see you next time.